Every atom in your body originated from a star that exploded billions of years ago, a testament to the profound connections woven throughout the cosmos. As we explore the formation of cosmic structures, our own solar system, and the tantalizing possibility of life beyond Earth, we join scientists in their quest to understand how the universe has evolved and how everything may have begun. The Big Bang Theory is the leading explanation for the origin of our universe, proposing that it began as an incredibly hot and dense point approximately 13.8 billion years ago. This singularity underwent a rapid expansion, leading to the formation of space, time, and ultimately, all the matter and energy that we observe today. The term Big Bang can sometimes be misleading, as it implies a cosmic explosion. However, this expansion was not an explosion in the traditional sense, as it happened everywhere at once. As the universe expanded, it cooled, allowing subatomic particles to form. Within a few minutes, these particles combined to create hydrogen and helium, the building blocks of stars and galaxies. This early stage of the universe is often referred to as the Hot Big Bang, characterized by extreme temperatures and densities. Over billions of years, gravity drew these gases together, leading to the formation of stars, galaxies, and the vast structures we see scattered across the cosmos. An essential piece of evidence supporting the Big Bang theory is the observation of cosmic microwave background radiation. This faint, uniform glow detected from all directions in space is considered the remnant heat of the early universe, providing a snapshot of the universe when it was just a mere fraction of a second old. Additionally, the redshift of distant galaxies exhibits that they are moving away from us, suggesting that the universe is still expanding, a phenomenon first observed by Edwin Hubble in the early 20th century. The Big Bang theory has evolved, incorporating findings from various fields of physics and astronomy. As research continues, scientists delve deeper into the conditions that existed in those early moments and the mechanisms governing the expansion and evolution of the universe. Understanding the Big Bang not only explains our cosmic origins, but also helps illuminate the fate of the universe itself, as researchers explore whether it will continue to expand indefinitely or if it may one day contract. The Big Bang theory is supported by several key pieces of scientific evidence that paint a compelling picture of the universe's origins. One of the cornerstone pieces of this evidence comes from the cosmic microwave background radiation. This faint glow, which fills the entire universe, is a remnant from the early hot state of the universe, roughly 380,000 years after the Big Bang. Detected in the 1960s, this radiation exhibits a nearly uniform distribution, suggesting that the universe was once in a very hot and dense state, which aligns perfectly with the predictions made by the Big Bang theory. Another important piece of evidence lies in the observable redshift of distant galaxies. When we look at galaxies far away, we notice that their light is shifted toward the red end of the spectrum. This shift indicates that these galaxies are moving away from us, which implies that the universe is expanding. This expansion was first observed by Edwin Hubble in the early 20th century, and it supports the notion that the universe started from a singular, highly concentrated point. The expansion can be traced back to a time when all matter and energy were packed into an incredibly small volume, supporting the concept of the Big Bang. Additionally, the ratios of light elements, such as hydrogen, helium, and lithium, provide further validation of the Big Bang model. The theory predicts specific proportions of these elements based on how they formed during the first few minutes of the universe's existence, known as nucleosynthesis. Observations reveal that the observed abundances of these elements in the cosmos align remarkably well with those predictions, reinforcing the validity of the theory. Lastly, the large-scale structure of the universe also adds to the evidence. The distribution of galaxies and galaxy clusters across the cosmos appears to follow patterns that can be traced back to the fluctuations in density present in the early universe. These structures have evolved over billions of years under the influence of gravity, consistent with the evolution expected from a Big Bang origin. As our understanding of the universe deepens, the evidence supporting the Big Bang theory continues to grow, shaping our comprehension of cosmic history. Cosmic microwave background radiation, often referred to as CMB, serves as a crucial snapshot of the universe approximately 388,000 years after the Big Bang. At this juncture, the universe had cooled enough for protons and electrons to combine and form neutral hydrogen, allowing photons to travel freely. These primordial photons are the remnants of that early stage, and they provide invaluable insight into the conditions of the young universe. When we measure the CMB, we observe a uniform glow that permeates all of space. However, slight temperature fluctuations exist within this radiation, revealing a wealth of information. These variations indicate the density differences in the matter that existed just after the Big Bang. Analyzing these fluctuations enables scientists to glean important data about the composition of the universe. For instance, we gain insights into the amounts of dark matter and dark energy, both of which play significant roles in governing the universe's structure and expansion. Additionally, the CMB allows scientists to test and refine cosmological models. The data helps confirm the Big Bang theory, as it aligns with predictions about the universe's expansion and the formation of large-scale structures. Detailed measurements from missions like the Wilkinson Microwave Anisotropy Probe and the Planck satellite have revealed the universe's age, which is estimated to be around 13.8 billion years, and have provided a clearer understanding of its evolution over time. Furthermore, the CMB acts as a cosmic ledger, recording the events of the universe's infancy, including the growth of galaxies and cosmic inflation. This inflationary period, a rapid expansion that occurred moments after the Big Bang, is supported by the uniform distribution and patterns detected in the CMB. As a result, the study of cosmic microwave background radiation continues to be a cornerstone of cosmology, unlocking mysteries about the universe and laying the groundwork for future discoveries. Dark matter has been a crucial player in the formation and evolution of our universe. Although it cannot be observed directly, its presence is inferred through its gravitational effects on visible matter, and it makes up approximately 26% of the total mass-energy content of the cosmos. Without dark matter, the structure we see in the universe today would likely not exist as we know it. In the early universe, shortly after the Big Bang, conditions were hot and dense, with particles flying around at unimaginable speeds. As the universe expanded and cooled, matter began to coalesce under the influence of gravity. This is where dark matter came into play. Unlike ordinary matter, which interacts electromagnetically, dark matter does not emit, absorb, or reflect light, making it invisible and only detectable through its gravitational influence. It provided the scaffolding upon which visible matter could gather, helping to form the first stars and galaxies. The presence of dark matter explained why galaxies rotate at the speeds they do. The gravitational pull of visible matter alone is insufficient to account for the high rotation speeds in the outer portions of galaxies. Dark matter extends well beyond the visible boundaries of galaxies, creating vast halos of gravitational influence that hold the galaxies together. This invisible mass assists in the overall structure formation, leading to the cosmic web of filaments and voids we see today. Moreover, dark matter is thought to influence the expansion of the universe. Research into its properties and effects helps astrophysicists understand concepts like gravitational lensing, where light from distant objects bends around massive structures, providing key insights into the distribution of dark matter. By studying the interplay between dark matter and visible matter, scientists continue to unlock the mysteries of how our universe has come to be, showcasing dark matter's essential role in the grand cosmic narrative. Advancements in technology over the past few decades have tremendously reshaped our understanding of the universe's birth, a moment known as the Big Bang. The development of powerful telescopes has allowed us to observe distant galaxies and cosmic phenomena that were once only theoretical. For instance, the Hubble Space Telescope, launched in 1990, has provided stunning images and crucial data that have helped refine our knowledge of cosmic expansion and the age of the universe. Another groundbreaking technological advancement is the detection of cosmic microwave background radiation, which is the afterglow of the Big Bang. Satellites like the Wilkinson Microwave Anisotropy Probe and the Planck satellite have mapped variations in this radiation with incredible precision. These measurements offer a snapshot of the universe when it was just 380,000 years old and have been instrumental in confirming predictions made by the Big Bang theory. Through such analysis, scientists can estimate the universe's age to roughly 13.8 billion years and gain insights into its early conditions. Moreover, gravitational wave astronomy has introduced a new way of observing the universe. The Laser Interferometer Gravitational Wave Observatory, which began detecting gravitational waves in 2015, has opened up a fresh perspective on cosmic events. These ripples in space-time help scientists study phenomena such as merging black holes and neutron stars, allowing for a deeper understanding of how stars formed and evolved in the cosmos, which ties back to the conditions that followed the Big Bang. The combination of these technological advancements has not only expanded our observational capabilities, but also fostered theoretical development. Computer simulations increasingly model cosmic evolution, helping to bridge gaps between observational data and theoretical predictions. Thanks to technology, our understanding of the universe's birth has evolved from speculative ideas to a rich tapestry of interconnected discoveries, pushing the limits of what we know about our origins in the cosmos. A galaxy is a vast system consisting of stars, stellar remnants, interstellar gas and dust, and dark matter, all bound together by gravitational forces. The number of stars within a galaxy can range from a few billion to 100 trillion or more, depending on its size and type. Galaxies come in various forms, including spiral, elliptical, and irregular, each characterized by distinct structures and star distributions. The formation of galaxies is a process that unfolds over billions of years. It typically begins with the cooling and condensation of gas in the early universe. Around 300 million years following the Big Bang, small fluctuations in density led to regions where matter began to clump together. As these clouds of gas accumulated more material, the gravitational forces intensified, triggering the formation of stars. As these stars continued to form, they interacted with their surroundings. In spiral galaxies, for example, stars and gas rotate around a central core, creating a structure with distinct arms. In contrast, elliptical galaxies often emerge from the merger of smaller galaxies, leading to a more uniform distribution of stars without the prominent structures seen in spirals. Over time, galaxies also evolve through processes like star formation and the eventual death of stars, resulting in the creation of new elements and materials that further enrich the galaxy's composition. Interactions with other galaxies can lead to mergers, dramatically altering their structure and star population. This interplay between formation, evolution, and interaction is what makes galaxies dynamic systems, continually shaping the very fabric of our universe. Galaxies are classified based on their shape and structure, a system that was pioneered by astronomer Edwin Hubble in the early 20th century. Hubble devised a classification scheme known as the Hubble sequence, which divides galaxies into several distinct categories: spiral, elliptical, and irregular. This categorization provides insights into their formation and evolution. Spiral galaxies, as the name suggests, have a distinct spiral structure. They are characterized by their rotating disks that contain stars, gas, and dust, along with a central bulge surrounded by a halo of stars. The arms of spiral galaxies are where most star formation occurs, often resulting in a beautiful distribution of bright and young stars. Examples include the Milky Way and the Andromeda Galaxy, both of which display this spiral elegance. On the other hand, elliptical galaxies exhibit a more rounded shape and lack the striking features of spirals. They can range from nearly spherical to elongated forms and are often composed of older stars with minimal interstellar gas and dust. This composition means that star formation in elliptical galaxies is generally low, resulting in a population dominated by red and yellow stars. They are thought to be the product of galaxy mergers, where two or more galaxies collide and coalesce over time. Finally, irregular galaxies do not fit neatly into the spiral or elliptical categories. They often have irregular shapes and structures arising from gravitational interactions or disruptions, such as those caused by nearby galaxies. Their chaotic appearance is coupled with ongoing star formation, making them vibrant and diverse. Overall, this classification system plays a crucial role in understanding the immense variety and complexity of galaxies throughout the universe. Superclusters are some of the largest known structures in the universe, comprising groups of galaxies bound together by gravity. They play a vital role in the cosmic web, which is the large-scale structure of the universe formed by galaxy clusters, superclusters, filaments, and voids. These massive formations serve as critical markers of how matter is distributed on grand scales and provide insights into the nature of gravity and the expansion of the universe. A fascinating aspect of superclusters is that they reveal the influence of dark matter and dark energy. While we cannot see dark matter directly, its presence can be inferred from the gravitational effects it has on galaxies within superclusters. This relationship helps astronomers understand not only the distribution of visible matter, but also the underlying forces that govern their movements. Studies of superclusters suggest that these structures can contain hundreds of thousands of galaxies, sprawled across distances that can reach over 1 billion light-years, emphasizing their monumental scale. Furthermore, the formation and evolution of superclusters relate directly to the history of the universe itself. They began to form billions of years ago, shortly after the Big Bang, as small fluctuations in the density of matter led to gravitational collapse, causing galaxies to clump together over time. As they evolve, superclusters can shed light on how galaxies interact, merge, and evolve, offering a glimpse into the future of our cosmic neighborhood. Superclusters also provide a backdrop for examining the universe's directional behavior. They influence the paths of galaxies and help astronomers map out the overall structure of the universe. By understanding these colossal structures, scientists gain a deeper appreciation for the universe's complexity and the fundamental processes that have shaped it throughout its history. Black holes, particularly the supermassive ones found at the centers of most galaxies, exert a profound influence on their surrounding environments. These colossal entities can contain mass equivalent to millions or even billions of suns, creating extreme gravitational pulls that shape the dynamics of nearby stars and gas. The gravitational attractions of black holes can lead to the stabilization of galaxy structures, regulating the orbits of stars and other matter that resides in the galaxy's core. Moreover, black holes are not merely passive observers. They can actively affect their surroundings through a process known as accretion. This occurs when gas and dust from the galaxy are drawn towards the black hole, forming an accretion disk. As this material spirals inward, it heats up to incredibly high temperatures, emitting intense radiation across the electromagnetic spectrum, particularly in X-rays. This radiation can impact star formation in the galaxy, often suppressing it by heating the surrounding gas, creating a feedback loop that limits how much new material can collapse into stars. In certain instances, as material is pulled into a black hole, it can also be expelled outward through powerful jets that emerge from the regions around the black hole. These jets can stretch vast distances into space, impacting the interstellar medium and seeding it with elements forged in the heart of dying stars. This energetic outflow may trigger new star formation in regions far removed from the black hole, while also disrupting existing stellar systems. Additionally, the role of black holes in the evolution of galaxies is being explored through the connection between supermassive black holes and the overall structure of their host galaxies. Research suggests that there may be a correlation between the mass of a black hole and the properties of the stars in its galaxy, leading scientists to consider that black holes could play a crucial role in galaxy formation and growth. The intricate dance between black holes and their galaxies continues to be a fundamental topic in the study of cosmic evolution. Quasars, or quasi-stellar objects, are incredibly luminous celestial bodies powered by supermassive black holes at the centers of distant galaxies. These black holes consume surrounding gas and dust, releasing tremendous amounts of energy in the form of light across the electromagnetic spectrum. A single quasar can outshine an entire galaxy, making these objects some of the brightest in the universe. The importance of quasars in cosmology cannot be overstated. They serve as beacons that illuminate our understanding of the early universe. As we observe quasars that are billions of light years away, we are actually looking back in time. This allows astronomers to gather crucial information about the conditions of the universe when it was much younger, particularly during a period known as the cosmic noon. At this time, which occurred around 11 billion years ago, star formation rates were at their peak, and quasars played a significant role in shaping galaxies. Quasars also provide insights into the expansion of the universe. Studying their light has helped scientists measure the rate of this expansion, enhancing our understanding of dark energy, the mysterious force driving the acceleration of this expansion. Moreover, the distribution of quasars across the universe reveals important details about the formation and evolution of cosmic structures over time. In addition to their scientific importance, quasars challenge our perceptions of the universe's size and age. They remind us that even at astounding distances, we can still witness the aftermath of events that occurred billions of years ago, bridging the gap between the past and present. As research continues to evolve, quasars remain key to unraveling the mysteries of the cosmos. The formation of our solar system began with a vast cloud of gas and dust known as the solar nebula. This nebula, primarily composed of hydrogen and helium, was the remnants of previous stars that had exploded in supernovae. Over several million years, various cosmic events triggered instabilities within the nebula, causing it to collapse under its own gravity. As the cloud contracted, it began to spin, forming a flattened disk shape due to conservation of angular momentum. At the center of this spinning disk, material accumulated and heated up, ultimately forming the Sun. The immense gravitational force of the Sun caused it to draw in surrounding material, creating a solar wind that blew away lighter elements from the inner regions. Meanwhile, in the cooler outer regions of the disk, tiny particles of dust began to stick together, forming larger bodies known as planetesimals. These planetesimals continued to collide and merge over time, gradually building up protoplanets. Within this chaotic environment, the inner solar system produced rocky planets like Earth and Mars, while the outer regions gave rise to the gas giants like Jupiter and Saturn. The diversity of the planets and other celestial bodies arose from the varying conditions across the disk, such as temperature and chemical composition. Various phenomena, including gravitational interactions and the processes of accretion and differentiation, shaped the young solar system, leading to the configuration we observe today. The remnants of this stellar nursery can still be seen in the form of asteroids, comets, and other small celestial bodies that linger in the space between the planets. This fascinating process reflects the dynamic and ever-evolving nature of our universe. Terrestrial planets are primarily rocky and composed mostly of silicate rocks and metals, which gives them a solid surface. These planets, which include Mercury, Venus, Earth, and Mars, tend to be smaller in size compared to their gas giant counterparts. They have higher densities and generally exhibit a greater variety of geological features, such as mountains, valleys, and impact craters. Another defining characteristic of terrestrial planets is their relatively thin atmospheres, which can vary significantly in composition, with Earth being the most conducive to life. Gas giants, on the other hand, are mainly composed of hydrogen and helium, resulting in their lack of a solid surface. Jupiter and Saturn are prime examples of gas giants, with their vast atmospheres featuring swirling clouds and powerful storms, including the famous Great Red Spot on Jupiter. These planets are tremendous in size, often being over 10 times the diameter of Earth. Their densities are much lower than those of terrestrial planets because their mass is largely concentrated in gaseous form, which also creates a very deep atmosphere. Another key distinction lies in the presence of rings and moons. gas giants are often accompanied by extensive ring systems and numerous moons, which can number in the dozens or even hundreds. For instance, Saturn is renowned for its striking ring system, while Jupiter boasts many large moons, such as Ganymede, which is the largest moon in the solar system. Terrestrial planets typically have fewer moons, and if they do have them, those satellites tend to be smaller and less numerous. Lastly, the temperatures and weather patterns seen on these two types of planets vary drastically. Terrestrial planets are generally cooler in their outer layers due to their solid surfaces and thinner atmospheres, whereas gas giants can have extreme temperature gradients and complex weather systems as a result of their thick atmospheres and vast distances from the Sun. This combination of characteristics makes both classes of planets fascinating subjects in the study of our solar system and beyond. The moons of the planets exhibit a fascinating diversity in their formation and composition, reflecting a complex history of the solar system. Generally, moons can be grouped into three main categories based on their origin. The first group includes those that formed alongside their parent planets through a process known as co-formation. This is seen in larger moons that likely formed from the material that surrounded the young planet during its formation. An example of this is Earth's moon, which is believed to have been created from debris resulting from a massive impact with a Mars-sized body. The second category comprises moons that are thought to have formed independently in the protoplanetary disk and were later captured by the gravitational pull of a planet. This scenario is especially relevant for some of the smaller, irregular moons found around the gas giants like Jupiter and Saturn. These moons can often be composed of a mix of rock and ice, revealing insights into the conditions and materials present in the early solar system. The third group includes those moons that may have experienced significant alterations throughout their history. These can involve moons that started as larger bodies but were fractured by collisions, or those that underwent significant geological activity. For instance, Io, one of Jupiter's largest moons, is geologically active and is known for its sulfur-rich volcanic activity, making it a unique case among moons. When it comes to composition, the moons can vary greatly. Some, such as the icy moons of Saturn like Enceladus, contain substantial amounts of water ice and show signs of subsurface oceans, hinting at possible habitability. Others, like Titan, are enveloped in thick atmospheres rich in nitrogen, while still others, like the rockier moon Phobos of Mars, provide clues about their history and the processes that shaped them. Each moon tells its own story, contributing pieces to the puzzle of our solar system's formation and evolution. Recent discoveries about dwarf planets in our solar system have significantly expanded our understanding of these fascinating celestial bodies. One of the most intriguing findings comes from the observations of Pluto and its moons. Data gathered from the New Horizons spacecraft revealed that Pluto has a complex geological history characterized by icy mountains, possible subsurface oceans, and a surprisingly diverse range of surface materials. This level of geological activity challenges previous perceptions of Pluto as a cold, static body, highlighting that even distant worlds can exhibit dynamic behaviors. Another remarkable discovery involves the dwarf planet Haumea. Research has shown that Haumea spins remarkably fast, completing a rotation in just under 4 hours. This rapid rotation contributes to its distinctive elongated shape, resembling a giant cosmic football. Additionally, Haumea's surface is covered with crystalline ice, which forms due to the unique conditions surrounding this distant object. Observations of Haumea's moons also suggest a rich history and possible interactions with their parent body. Eris, another notable dwarf planet, has recently been found to have an atmosphere that expands and contracts as it moves closer to and further away from the Sun. This atmospheric behavior offers a fascinating glimpse into how distant, cold bodies can still engage in complex interactions with solar radiation. Moreover, the surface of Eris is believed to host a frozen layer of methane, suggesting the presence of organic compounds and hinting at possibilities for varied chemical processes. These discoveries collectively shine a light on the diversity and complexity of dwarf planets, challenging our existing models of planetary formation and evolution. By studying these distant objects, scientists are uncovering new insights into the processes that have shaped our solar system. Each revelation adds another layer to our understanding, positioning dwarf planets as crucial pieces in the broader puzzle of cosmic exploration. The atmosphere plays a pivotal role in determining a planet's potential to host life, as it affects everything from temperature regulation to the availability of essential elements. For a planet to support life as we know it, it typically needs a stable atmosphere that can maintain liquid water, protect against harmful radiation, and provide essential gases such as oxygen or carbon dioxide. Take Earth, for instance. Its atmosphere consists primarily of nitrogen and oxygen, creating a protective blanket that shields the surface from damaging ultraviolet radiation and helps regulate temperatures. This balance is crucial, as it allows for the presence of liquid water, which is considered a key ingredient for life. The atmosphere also acts as a medium for weather patterns, facilitating the distribution of heat and nutrients across the planet. In contrast, Mars presents an intriguing case. Its thin atmosphere, composed mostly of carbon dioxide, is unable to trap heat effectively, resulting in surface temperatures that are often frigid. While Mars has polar ice caps and evidence of ancient water flows, the harsh atmospheric conditions make it a challenging environment for life as we know it. Nevertheless, scientists continue to investigate the possibility of microbial life adapting to such extreme conditions. Then there is Venus, which has a dense, toxic atmosphere dominated by carbon dioxide and thick clouds of sulfuric acid. The intense greenhouse effect creates surface temperatures hot enough to melt lead. These extremes make it nearly impossible for life to exist as we understand it. However, researchers are exploring the idea of microbial life existing in the more temperate upper layers of Venus's atmosphere, showcasing just how crucial atmospheric composition is when considering a planet's potential for hosting life. Several remarkable missions have ventured to explore the planets in our solar system, providing us with invaluable insights into their nature and the conditions that exist beyond Earth. One of the earliest and most notable was the Mariner program, specifically Mariner 4, which made history in 1965 by becoming the first spacecraft to fly by Mars. It returned those unforgettable images of the Martian surface, revealing a desolate, cratered landscape and igniting curiosity about the red planet. Another major achievement came with the Viking missions in the 1970s. Viking 1 and Viking 2 not only orbited Mars, but also landed on its surface. These missions conducted extensive experiments to analyze the soil, search for signs of life, and gather data on the atmosphere and weather patterns. Their findings laid foundational knowledge for future explorations and even sparked debates about the potential for life beyond Earth. In the 1980s, planetary exploration saw a significant expansion with the Voyager missions. Voyager 1 and Voyager 2 not only traveled to the outer planets, but provided breathtaking images and data about Jupiter, Saturn, Uranus, and Neptune. Voyager 2, notably, became the only spacecraft to visit Uranus and Neptune, greatly enhancing our understanding of their atmospheres, moons, and rings. Most recently, the Mars rovers such as Spirit, Opportunity, Curiosity, and Perseverance have profoundly changed our perspective of Mars. Equipped with advanced scientific instruments, these rovers have explored the surface, investigated the planet's geology, and searched for signs of ancient microbial life. Each mission has contributed essential knowledge, paving the way for future explorations, including human missions to the Martian surface. These endeavors not only deepen our understanding of our solar system, but also raise intriguing questions about our place within it. Rovers such as Curiosity and Perseverance play a pivotal role in expanding our knowledge of Mars by conducting detailed investigations on the Martian surface. These robotic explorers are equipped with advanced scientific instruments that allow them to analyze soil, rock samples, and the atmosphere in ways that would be impossible from orbit or even through remote sensing. Each rover is designed with specific objectives that contribute enormously to our understanding of the planet's geology, climate, and potential for past life. Curiosity, which landed on Mars in 2012, has been primarily focused on understanding the planet's habitability. It has found evidence of ancient riverbeds, minerals formed in water, and organic molecules, essential components for life as we know it. Its findings have reshaped our perception of Mars, suggesting that it may have been conducive to life eons ago. Curiosity's detailed analyses offer insights into the planet's past climate and geological processes, which are crucial for understanding how Mars has changed over billions of years. The more recent rover, Perseverance, which landed in 2021, takes this knowledge further. One of its primary missions is to search for signs of ancient microbial life, as well as collect and cache samples to be returned to Earth by future missions. Equipped with new technology, Perseverance can analyze rock samples on the spot with unprecedented precision. Additionally, it carries the Ingenuity helicopter, which has demonstrated powered flight on another planet for the first time, opening up new possibilities for exploration. Through their discoveries, both Curiosity and Perseverance are not just enhancing scientific knowledge, but also laying the groundwork for future human exploration. Their findings provide critical information regarding the best sites for potential human landing missions and contribute to our ongoing quest to understand whether life ever existed beyond Earth. As these rovers continue to traverse the Martian landscape, they remind us that Mars is not merely a dusty, distant neighbor, but a world rich with history and mystery waiting to be unraveled. The Voyager missions, which launched in the late 1970s, have fundamentally transformed our understanding of the outer planets in our solar system. Voyager 1 and Voyager 2 provided us with unprecedented close-up images and data, revealing many details about these distant worlds. For instance, Voyager 2's journey to Uranus and Neptune unveiled their unique atmospheric characteristics, including Uranus's unusual tilt and Neptune's dynamic weather patterns, characterized by the fastest winds recorded in the solar system. One of the most surprising discoveries came from Voyager 2's flyby of Neptune, where scientists found a massive storm system in the atmosphere referred to as the Great Dark Spot. This storm bore similarities to Jupiter's Great Red Spot, highlighting the fascinating dynamics and complexities of these gaseous giants. Additionally, Voyager missions unveiled the presence of rings around Uranus and Neptune, further showcasing the diversity of ring systems in our solar system and prompting further questions about their origins and evolution. The missions also explored the moons of these outer planets, revealing remarkable geological features. For example, Triton, Neptune's largest moon, was found to be geologically active, with geysers erupting nitrogen gas, suggesting a complex internal structure. The exploration of Io, one of Jupiter's moons, demonstrated extraordinary volcanic activity, leading scientists to rethink our assumptions about the conditions that can foster geological processes in such a remote and cold region. These findings have not only expanded our knowledge of planetary science, but have also inspired future exploration. The data collected by Voyager missions continue to inform scientists about the composition, atmospheres, and potential habitability of celestial bodies, shaping ongoing research and missions dedicated to uncovering more secrets of the outer solar system. Astrobiology is a vital field in understanding the potential for life beyond Earth, especially as we explore exoplanets that may have conditions suitable for habitability. This branch of science combines biology, chemistry, geology, and astronomy to probe the various environments where life could exist. By studying the conditions necessary for life as we know it, astrobiologists can develop models to assess whether certain exoplanets might harbor life. When astronomers identify exoplanets within the so-called habitable zone, where conditions might allow liquid water to exist, astrobiology comes into play. Researchers investigate the atmospheres, surfaces, and potential geological activity of these worlds. They look for biosignatures, which are indicators that biological processes may be occurring. These might include gases like oxygen or methane, which, when found together in significant quantities, could suggest the presence of living organisms. Astrobiology also encourages us to think beyond our own experience of life on Earth. It prompts scientists to consider varied biochemical systems that might thrive in extreme environments, such as those found on some moons in our solar system. This broader perspective expands our search criteria for life, allowing for the evaluation of environments that were previously thought to be inhospitable. Ultimately, astrobiology is fundamental not just for locating potential life, but for understanding life's resilience and diversity across different planetary environments. Each mission to a potentially habitable exoplanet holds the possibility of unveiling processes that could transform our view of life itself, reshaping our understanding of where and how life can evolve across the cosmos. Telescopes designed specifically for exoplanet research utilize advanced techniques to uncover the secrets of distant worlds, including those that may resemble Earth. One crucial approach is known as the transit method. When a planet passes in front of its parent star from our perspective, it blocks a small amount of light, leading to a detectable decrease in the star's brightness. By monitoring this dimming over time, astronomers can determine the planet's size and orbit, providing essential clues about its potential habitability. A key characteristic of Earth-like planets is their position within the habitable zone, often referred to as the Goldilocks zone. This is the region around a star where conditions could allow liquid water to exist on a planet's surface. Telescopes equipped with precision photometers can measure brightness changes with remarkable accuracy, enabling scientists to ascertain whether a planet is in this crucial zone. Identifying Earth-sized planets within such regions raises the intriguing possibility of finding extraterrestrial life. Spectroscopy is another powerful tool employed by these specialized telescopes. This technique involves analyzing the light spectrum of a star and the light that filters through a planet's atmosphere during transits. By examining the chemical fingerprints of gases like carbon dioxide, oxygen, and methane, scientists can infer the planet's atmospheric composition. The presence of these gases can indicate potential biological processes, hinting at conditions that could support life as we know it. Furthermore, the advancements in telescope technology, such as adaptive optics and interferometry, have significantly enhanced our ability to directly image exoplanets, even those that orbit very close to their stars. These techniques mitigate the blurring effects of Earth's atmosphere, sharpening our view and providing more data about the planet's characteristics. In doing so, these telescopes do not merely help identify Earth-like planets, they expand our understanding of the universe and our place within it, stirring the imagination about what might be out there, waiting to be discovered. The concept of the multiverse proposes the existence of multiple, perhaps infinite universes beyond our own, each with its own distinct set of laws, constants, and physical realities. One of the key hypotheses stems from cosmic inflation, which suggests that during the universe's rapid expansion after the Big Bang, different regions could have undergone varying rates of inflation. This could lead to pockets of space that are separate from one another, forming entirely different universes that might not interact. Another intriguing hypothesis is based on quantum mechanics. The many worlds interpretation suggests that every time a quantum event occurs, the universe splits into different branches, each representing a possible outcome. This means there could be countless variations of reality existing simultaneously, where every choice or random event creates new universes where each scenario plays out differently. These ideas dramatically challenge our traditional understanding of a single universe, as they imply that our reality is just one of many. It raises profound philosophical and scientific questions about the nature of existence, the limits of human observation, and the very definitions of reality and probability. If multiple universes exist, it complicates the notion of fine-tuning, where certain physical constants seem perfectly calibrated for life. How does one explain these conditions when other universes might have entirely different sets of rules? The multiverse hypothesis also stimulates debate among physicists and cosmologists. While some argue it provides an elegant solution to unresolved questions in physics, others criticize it for being inherently untestable, casting doubt on its scientific validity. As research continues and our understanding of the universe evolves, the multiverse remains a tantalizing frontier that challenges our perceptions of reality and invites us to ponder the extraordinary possibilities that lie beyond our observable universe. String theory offers a novel approach to unify the primary fundamental theories of physics by suggesting that the fundamental building blocks of the universe are not point-like particles, but rather one-dimensional strings. These strings vibrate at specific frequencies, and their various vibrational modes correspond to different particles. This concept introduces a harmonious framework where the seemingly distinct particles of the Standard Model, which describes the electromagnetic and nuclear interactions, share a common origin. Traditional physics, including general relativity and quantum mechanics, often struggles to combine their principles. General relativity effectively describes the gravitational force and the structure of space-time, but it does not incorporate quantum phenomena. On the other hand, quantum mechanics dominates at the subatomic scale but fails to address gravity. String theory aims to bridge this divide by providing a consistent way to integrate gravity with quantum mechanics. It does this by incorporating gravity naturally into its framework, allowing for a universe where all forces, including gravity, can be described within a single theoretical model. Moreover, string theory predicts additional dimensions beyond the familiar 3 dimensions of space and 1 of time. To satisfy the mathematics that arise in string theory, scientists suggest that there could be up to 10 or 11 dimensions. While we do not directly observe these extra dimensions, their existence helps to reconcile the different forces of nature. The shapes and configurations of these dimensions could result in various manifestations of physical phenomena that we perceive in our 3-dimensional reality. The potential implications of string theory are profound. By providing a unified framework, string theory allows scientists to explore connections between particles, forces, and the very fabric of space-time itself. It remains a subject of intense research, as physicists seek evidence and further understanding of how these intertwined strings might elucidate the mysteries of the universe, and whether they can answer the ultimate question of why the laws of physics behave as they do. Quantum mechanics plays a crucial role in our understanding of cosmology by bridging the seemingly incompatible realms of the very small and the very large. At the heart of modern cosmology lies the quest to comprehend the behavior of the universe's fundamental building blocks, while also addressing the grand scale of cosmic structures. Quantum mechanics provides a framework that helps explain phenomena such as the behavior of particles in high-energy conditions, especially those present in the early universe moments after the Big Bang. One fascinating aspect of quantum mechanics is its introduction of uncertainty and wave-particle duality. These principles become increasingly significant when we extrapolate physics to extreme environments, like black holes or the earliest moments of our universe. For instance, the concept of quantum fluctuations suggests that tiny variations in energy levels could lead to the formation of structures like galaxies. This idea has enabled scientists to explore the rapid expansion known as cosmic inflation, a theory that posits the universe underwent a remarkable growth spurt shortly after the Big Bang, driven by these quantum effects. Moreover, quantum mechanics offers insights into the nature of gravity through theories like quantum gravity and string theory. These approaches attempt to unify general relativity, which governs macroscopic phenomena, with quantum mechanics, which describes the microcosm. Such unification is critical for understanding the behavior of space-time in extreme conditions, such as near singularities where classical physics breaks down. Researchers are continually investigating these theories, striving to reveal deeper truths about the universe's functioning. Additionally, developments like quantum entanglement challenge traditional notions of distance and locality in cosmology. This phenomenon suggests that particles can be interconnected in a manner where the state of one instantly influences another, regardless of the distance separating them. Such intricacies prompt cosmologists to rethink the very fabric of space-time, highlighting how quantum mechanics enriches and complicates our comprehension of cosmic existence. The interplay between these fields continues to inspire new research, illuminating the enigmatic connections that weave together the structure of our universe. Wormholes represent a fascinating concept in theoretical physics that suggests a shortcut through the fabric of space-time, potentially allowing travel between distant points in the universe. Imagine the universe as a 2-dimensional surface. When you fold that surface, two distant points can be brought close together. A wormhole is thought to act in a similar way, connecting two separate points in space-time, making what seems impossible, instantaneous travel over vast distances, potentially feasible. The idea of wormholes arises from Einstein's theory of general relativity, which describes how gravity affects the shape of space-time. In theory, these passages, sometimes referred to as Einstein-Rosen bridges, could allow an object to enter one end of a wormhole and emerge from the other almost instantaneously. However, the stability of such structures is a significant issue. Most theoretical models suggest that wormholes would collapse before anything could actually travel through them, making them intriguing but not yet practical. To further complicate matters, traversable wormholes would require exotic matter which has negative energy density. This type of matter would counteract the gravitational forces that threaten to close off the wormhole. While this type of exotic matter has not yet been observed in our universe, the concept stimulates extensive research and discourse regarding the possibilities of space travel. While wormholes remain entirely theoretical and are often relegated to the realm of science fiction, they challenge our understanding of the universe and how we might one day navigate its vastness. As our exploration of the cosmos continues, wormholes stand out as a tantalizing idea that blurs the lines between science and imagination, making us wonder just how far we are from the stars. Cosmic inflation, a theory that proposes a rapid expansion of the universe in its earliest moments, has profound implications for our understanding of the universe's shape. This dramatic expansion suggests that, despite the observable universe appearing finite, it is part of an infinite cosmos. During inflation, regions that are now separated by vast distances were once in close proximity. As a result, the uniformity we observe in the cosmic microwave background radiation indicates that the universe may be flat on large scales. The concept of a flat universe means that geometry follows the rules of Euclidean space, where parallel lines never converge. Inflationary theory posits that any initial curvature would have been smoothed out during this extreme expansion. Consequently, while the universe can emerge with various shapes, like closed, open, or flat, most evidence leans towards a flat universe, suggesting that it extends infinitely in all directions. Such a structure allows for complexities like galaxies and clusters to form while maintaining a consistent cosmic background radiation. Interestingly, the distribution of cosmic structures is influenced by the underlying shape of the universe. A flat universe leads to a more uniform spread of matter and energy, allowing for the large-scale structure we observe today. In an infinite universe, galaxies could continue to form indefinitely, as there is no edge or center, disrupting the notion of boundaries and limits in cosmic evolution. Furthermore, understanding the implications of cosmic inflation also raises questions about the ultimate fate of the universe. If the universe is flat and continues to expand, it may lead to a scenario where galaxies drift apart eternally. This potential future scenario sparks curiosity about the nature of reality itself and whether there are areas beyond our observable universe, possibly containing different physical properties or even different laws of nature. The interplay between inflation, shape, and the fate of the universe continues to be an exciting frontier in cosmology. Dark energy is a mysterious force that is believed to make up approximately 70% of the universe. Its presence was first inferred in the late 20th century when astronomers observed the unexpected acceleration in the expansion of the universe. Instead of slowing down due to gravity, galaxies appear to be moving away from each other at an ever faster rate, indicating that something unseen is working against gravitational attraction. This elusive energy acts like a repulsive force, pushing galaxies apart over vast distances. The leading theory posits that dark energy has a constant density, even as the universe expands. This means that as more space is created between galaxies, more dark energy fills that space, leading to an ongoing acceleration of the universe's expansion. Essentially, dark energy can be thought of as a type of cosmic anti-gravity. One of the prominent explanations for dark energy is that it is related to the energy of empty space, or vacuum energy. According to quantum theory, even the emptiest regions of space are teeming with tiny fluctuations in energy. However, the precise nature of dark energy remains one of the biggest puzzles in modern cosmology. Various hypotheses have been proposed, including modifications to gravitational theory, but none have yet succeeded in fully explaining its properties. The implications of dark energy extend far beyond our immediate understanding of the cosmos. As the universe continues to expand and dark energy persists, it raises profound questions about the ultimate fate of the universe. Could it lead to an eternal expansion, or might it eventually result in a big crunch? The answers remain one of the most exciting pursuits in the field of astrophysics, as scientists strive to unlock the secrets of dark energy and its role in shaping the universe as we know it. Scientists employ a variety of ingenious methods to study phenomena that cannot be observed directly, like dark matter, which remains invisible even to the most powerful telescopes. One of the primary approaches is through the observation of the gravitational effects that dark matter has on visible objects in the universe. For instance, astronomers carefully observe the rotation curves of galaxies. They have found that the outer regions of galaxies rotate much faster than what would be expected based solely on the visible matter. This discrepancy suggests the presence of unseen mass, namely dark matter, influencing the gravitational dynamics. Another technique involves the study of cosmic microwave background radiation, the afterglow of the Big Bang that fills the universe. Scientists analyze tiny fluctuations in this radiation, which can reveal information about the distribution of matter in the early universe. These fluctuations provide clues about how much dark matter existed and its role in the formation of large-scale structures, such as galaxy clusters. By understanding these patterns, researchers can deduce the broader effects of dark matter despite its elusive nature. Gravitational lensing is yet another method that scientists utilize. When light from distant galaxies passes near massive objects, the path of the light bends due to the gravitational field created by the mass. This phenomenon allows astronomers to infer the presence of dark matter surrounding these massive objects, as it bends the light more than the visible mass would suggest. By measuring the extent of this lensing effect, researchers can estimate the distribution and quantity of dark matter in a given area. Finally, particle physicists conduct experiments in laboratories to search for potential candidates for dark matter particles. They explore theories that might explain what dark matter is made of and look for rare interactions between dark matter particles and ordinary matter. These experiments, combined with astronomical observations, create a multifaceted approach to understanding one of the universe's greatest mysteries, opening doors to exciting new discoveries about the fabric of reality itself. Gamma-ray bursts are extremely energetic explosions that occur in distant galaxies, releasing more energy in a few seconds than the Sun will emit over its entire lifetime. These bursts are characterized by their intense gamma-ray radiation and can last anywhere from a fraction of a second to several minutes. This immense release of energy is thought to originate from catastrophic events, such as the collapse of massive stars or the merger of neutron stars, resulting in phenomena that create highly directed jets of radiation. The sheer force of gamma-ray bursts makes them among the most powerful events in the universe. They can emit gamma rays that travel billions of light-years through space, striking Earth with radiation that can momentarily outshine an entire galaxy. When such a burst occurs, it can trigger a cascade of reactions in the interstellar medium, leading to the creation of new elements and potentially influencing star formation in surrounding regions. Interestingly, gamma-ray bursts can be detected from immense distances, allowing astronomers to study the early universe. Some bursts exhibit signs of being linked to the deaths of very massive stars, which end their life cycle in spectacular explosions known as supernovae. Others may result from the merger of compact objects such as neutron stars, producing gravitational waves along with gamma-ray emissions. Due to their intensity and rare occurrences, gamma-ray bursts are not only fascinating to study, but also provide critical insights into the life cycles of stars and the evolution of galaxies. Their power and the stunning scale at which they operate underscore the dynamic and violent nature of our universe. reminding us just how small our world is in comparison to the cosmic fabric that surrounds us. Gravitational waves are ripples in the fabric of space-time, generated by some of the most violent and energetic processes in the universe. They occur when massive objects accelerate, such as when black holes collide or neutron stars merge. When these colossal shifts happen, they produce waves that propagate outward at the speed of light. These waves are incredibly faint, requiring sensitive instruments to detect them, but when captured, they open a new window into astrophysics. The detection of gravitational waves provides profound insights into events that were previously hidden from traditional observations. For instance, the merger of two black holes, which might not emit light, creates gravitational waves that can tell us about the mass and spin of the black holes involved. Scientists can glean critical information regarding the history and dynamics of such cosmic events, significantly enhancing our understanding of the underlying physics. Observatories like LIGO and Virgo have made groundbreaking discoveries through the observation of these waves. In 2015, LIGO detected gravitational waves for the first time, confirming a key prediction of Albert Einstein's general theory of relativity. Since then, multiple events have been recorded, shedding light on phenomena like the formation of heavy elements in the universe and the nature of neutron stars. Each detection brings with it the potential to unravel mysteries about the universe's most extreme conditions. As we continue to refine our detection capabilities and expand our observational reach, gravitational waves could revolutionize our understanding of the cosmos. They allow us to observe the universe in a completely new way, offering clues to its formation, structure, and the fundamental laws that govern it. The exploration of gravitational waves is a reminder of how much there is still to learn in the expansive sciences of cosmology and astrophysics. Dark matter and dark energy are two of the great enigmas of modern cosmology, both integral to our understanding of the universe yet profoundly mysterious. Dark matter, which makes up about 27% of the universe's total mass and energy content, is believed to be composed of particles that do not emit, absorb, or reflect light. This makes it invisible to current telescopes. Its presence is inferred from its gravitational effects on visible matter, such as galaxies and clusters of galaxies. For instance, the way galaxies rotate suggests there is far more mass present than we can see. On the other hand, dark energy accounts for approximately 73% of the universe. It is thought to be responsible for the acceleration of the universe's expansion. In the late 20th century, astronomers observed that distant galaxies are not only moving away from us, but doing so at an increasing speed. This unexpected finding led to the hypothesis of dark energy, a force that counteracts gravity on cosmic scales. While we understand that dark energy exists and affects the universe's expansion, its nature remains elusive, leading scientists to explore various theories, including the cosmological, constant, and dynamic fields. The relationship between dark matter and dark energy is complex yet fascinating. Both elements influence the structure and fate of the universe, but they do so in different ways. Dark matter strengthens gravitational attraction, pulling matter together to form galaxies and larger structures, while dark energy, in contrast, acts against this attraction. It drives the acceleration of the universe's expansion, distorting how we perceive space and time on a large scale. Researchers continue to investigate how these two components interact. Some theories propose that understanding dark matter might provide clues about dark energy, as both are linked to the fundamental nature of space and time. As our observational techniques improve and our theories evolve, the mysteries of dark matter and dark energy could offer profound insights into the very fabric of the cosmos, challenging our understanding and reshaping our place within it. Multiple missions to Mars have focused on the search for microbial life, which has fascinated scientists for decades. One of the cornerstone endeavors was the Viking program in the 1970s, where two landers conducted experiments designed to detect organic materials and biological activity in the Martian soil. One significant experiment involved mixing soil samples with hot nutrient broth, to see if anything would produce gas as an indication of metabolic processes. Interestingly, some gas was detected, yet the results remain debated, as they could be explained by purely chemical reactions rather than biological ones. In the early 2000s, the Mars exploration rovers, Spirit and Opportunity, further investigated the planet's geology and searched for signs of past water, which is crucial for life as we know it. They discovered hematite and other minerals that formed in watery environments, hinting at a time when Mars might have been more hospitable. The Curiosity rover, which landed in 2012, carried advanced laboratory instruments to conduct in situ analysis of Martian soil and rock. This rover detected organic molecules in rock samples and provided evidence of ancient environments that could have supported microbial life. The Mars 2020 mission, which launched the Perseverance rover, took the search for microbial life to new heights. Its goal includes looking for signs of ancient life in Jezero crater, a location believed to have once housed a large lake. Perseverance employs a suite of scientific instruments aimed at identifying biosignatures, the chemical indicators of biological processes. Among its innovations is the sample caching system, which collects, seals, and stores Martian soil and rock samples for future return missions. Each of these missions has contributed to our understanding of the Martian environment and the potential for life. Although definitive proof of current or past microbial life has not yet been found, the evidence garnered from these experiments builds a compelling case for continued exploration of the red planet. As we delve deeper into the Martian mysteries, we inch closer to answering the profound question of whether we are alone in the universe. Scientists are actively searching for various biosignatures, which are indicators of life, on exoplanets located beyond our solar system. One of the most prominent biosignatures is oxygen. On Earth, oxygen is continuously produced as a byproduct of photosynthesis, leading scientists to consider its presence in an exoplanet's atmosphere as a strong indicator of biological activity. The balance of oxygen with methane, another gas that tends to break down when combined with oxygen, could further suggest a dynamic process that supports life. Another promising biosignature is the detection of water vapor. Liquid water is essential for life as we know it, and finding water in the atmosphere of an exoplanet enhances the likelihood of a habitable environment. Additionally, scientists examine the presence of carbon dioxide and ozone. Carbon dioxide can indicate geological activity and the potential for biological processes, while ozone, which forms when oxygen interacts with ultraviolet light, hints at complex atmospheric chemistry that might arise from life. Planetary scientists also look for the spectral fingerprints of other potential biosignatures, such as signs of organic molecules like amino acids or fatty acids. These complex molecules are the building blocks of life, and their presence could suggest the conditions necessary for life to flourish. Exploring these indicators is a crucial part of the ongoing search for extraterrestrial life, bridging the gap between our understanding of biology and the diverse worlds found throughout the cosmos. Furthermore, scientists utilize advanced telescopes and instruments to study the light spectra from exoplanets. By analyzing how light interacts with a planet's atmosphere, they can identify the specific wavelengths absorbed or emitted by gases present there. This technique allows researchers to better understand not just the physical and chemical conditions on these distant worlds, but also the likelihood of life existing beyond our own. With every new planet studied, we draw closer to answering one of humanity's most profound questions. Are we alone in the universe? Extremophiles are organisms that thrive in environments once thought to be inhospitable to life, existing in extreme conditions such as intense heat, extreme cold, high acidity, or even high radiation. The existence of these remarkable creatures, found in places like deep-sea hydrothermal vents or the frozen landscapes of Antarctica, expands our understanding of the diverse conditions under which life can survive. By studying extremophiles, scientists gather valuable insights into the adaptability and resilience of life, which poses important implications for searching for extraterrestrial life. For instance, the robust nature of extremophiles suggests that life could potentially exist in similarly extreme settings beyond Earth. Moons like Europa with its icy surface and subsurface ocean, or Mars with its harsh environment, may host microbial life forms akin to those found in Earth's most extreme habitats. These findings lead researchers to speculate that if life can thrive in such extremophilic conditions on our planet, the possibilities for finding life elsewhere in the universe are much broader than previously imagined. Furthermore, the biochemistry of extremophiles reveals various survival strategies that can withstand environmental stress. From heat shock proteins that protect cells from high temperatures to unique metabolic pathways that allow organisms to extract energy in nutrient-scarce environments, these adaptations provide essential clues for astrobiologists. Understanding these mechanisms is crucial when it comes to designing missions to other planets and moons, as it allows scientists to formulate hypotheses about what types of life might be out there and how they could be detected. The implications of these hardy organisms extend beyond just identifying potential habitats for life. They also inspire the technologies we develop for exploration. By mimicking the resilience of extremophiles, scientists are creating instruments that can endure the harsh conditions of space environments. Each discovery about extremophiles not only adds another piece to the puzzle of life's origins, but also enhances our toolkit for searching for signs of life beyond our home planet. Recent astrobiological research has unveiled fascinating possibilities regarding the existence of life beyond Earth. One significant area of study revolves around the icy moons of the gas giants in our solar system. For example, Europa, one of Jupiter's moons, possesses a subsurface ocean beneath its icy crust. The detection of plumes of water vapor ejected into space by Europa suggests that this ocean might harbor the necessary conditions for life, such as warmth and chemical ingredients. Similarly, Saturn's moon Enceladus has gained attention due to its own subsurface ocean and geysers that spew water vapor and organic molecules. The analysis of the materials found in these plumes indicates a rich chemistry that mirrors certain elements crucial for life as we know it. Additionally, gravitational measurements indicate that Enceladus's ocean may be in contact with its rocky core, which could facilitate the complex chemistry that underpins life. Mars has also been a focal point for recent astrobiology studies. The discovery of seasonal dark streaks, known as recurring slope lineae, on the Martian surface suggests the possible presence of liquid salt water during warmer months. Recent rover missions, particularly the Perseverance rover, are actively searching for signs of ancient microbial life and collecting rock samples that may reveal more about the planet's past conditions. Extraterrestrial research has expanded beyond our solar system. Scientists have discovered numerous exoplanets located in habitable zones, where conditions are potentially right for liquid water. The study of atmospheres of these distant worlds through spectrometry has identified chemical signatures like methane and carbon dioxide, hinting at biological processes. As techniques and technologies advance, the prospect of discovering life elsewhere in the universe becomes increasingly plausible, igniting the imaginations of scientists and enthusiasts alike. Water is often referred to as the universal solvent, and its role in the search for extraterrestrial life is absolutely critical. Scientists believe that wherever there is liquid water, there is a higher likelihood of finding life. This is because water is essential for the biochemical reactions that sustain living organisms. It serves as a medium for transporting nutrients, a participant in metabolic processes, and a key component of biological structures. In our own solar system, celestial bodies such as Mars and the icy moons of Jupiter and Saturn, including Europa and Enceladus, have been identified as potential havens for life due to the presence of water in various forms. Mars, for instance, has evidence of ancient riverbeds and polar ice caps, suggesting that it once had liquid water on its surface. Meanwhile, the icy crusts of Europa and Enceladus conceal vast oceans beneath their surfaces, raising the tantalizing possibility that microbial life might exist in these hidden environments. Beyond our solar system, astronomers often look for exoplanets located within a region known as the habitable zone, where temperatures allow for liquid water to exist. The discovery of planets with Earth-like conditions, including the presence of water, significantly increases the chances of finding life as we know it. These factors make water not only a crucial element in our own biology, but also a key indicator in the quest to identify alien worlds that could support life. While water is essential, it is not the only requirement for life. Other conditions, such as the presence of organic molecules, suitable temperatures, and a source of energy, also matter. However, in the search for extraterrestrial life, the existence of water remains a primary focus, guiding researchers in their explorations of the universe and the search for life beyond Earth. Several exciting missions are on the horizon that promise to deepen our understanding of the solar system. One of the most anticipated missions is NASA's Artemis program, which aims to return humans to the Moon by the year 2025. This initiative will not only mark humanity's return to lunar exploration, but also serve as a stepping stone for future manned missions to Mars. The data collected from the Moon will help scientists learn more about its geology, resources, and the potential for long-term human habitation. Another noteworthy mission is the European Space Agency's Jupiter Icy Moons Explorer, often referred to as JUICE. Scheduled for launch in the year 2023, JUICE is designed to investigate 3 of Jupiter's largest moons, Europa, Ganymede, and Callisto. These icy worlds are of particular interest because they hold the potential for subsurface oceans, which could harbor conditions suitable for life. JUICE will employ advanced instrumentation to study these moons' ice shells, subsurface oceans, and surface compositions, providing invaluable insights into their habitability. NASA's Dragonfly mission is another groundbreaking endeavor, planned to launch in the year 2027. This innovative mission will send a rotorcraft lander to explore Titan, Saturn's largest moon. Titan is unique due to its dense atmosphere and the presence of liquid methane lakes on its surface. Dragonfly will fly to various locations on Titan, conducting science experiments and analyzing its organic chemistry, which is fundamental to understanding the complexities of prebiotic environments. Additionally, the United Arab Emirates has announced plans for a Mars mission named the Mars Ice Mission. Set to launch sometime in the late 2020s, this mission will aim to locate and study water ice on the Martian surface, offering vital data on the availability of this resource for future human colonization efforts. Together, these missions represent a new era of exploration that promises to answer long-standing questions about our cosmic neighborhood and potentially expand our search for life beyond Earth. International cooperation is profoundly shaping the future of space exploration in numerous ways, fostering collaboration that extends our reach beyond Earth. Countries that were once isolated in their space endeavors are now coming together to share knowledge, expertise, and resources. This synergy is essential for tackling the complex challenges of exploring distant planets, asteroids, and the lunar surface, where the scale and cost of missions often require collective effort. One of the most notable examples of this collaboration is the International Space Station, where astronauts from various countries work side by side, conducting experiments that improve our understanding of science in microgravity. The station serves as a model for what can be achieved when nations unite their resources and talents. As we plan for future missions to Mars and beyond, this precedent provides a powerful framework for cooperation, allowing each nation to contribute its unique strengths and technologies. Additionally, international partnerships are instrumental in developing next-generation spacecraft and technologies. For instance, the Artemis program aims to return humans to the Moon with contributions from space agencies around the world. By combining efforts, sharing data, and pooling financial resources, we can accelerate development and enhance safety. This collaborative approach not only lowers costs, but also enriches the scientific output of missions, as diverse perspectives lead to innovative solutions. Moreover, the shared exploration of space may foster peace and stability on Earth. When countries collaborate on ambitious projects, they build relationships that can transcend geopolitical tensions. The shared goal of discovering the cosmos inspires a sense of unity, and as humanity ventures further into the solar system, the benefits of cooperation could extend beyond science, potentially influencing international relations for the better. To venture beyond our own planet and explore others, several significant technological advancements are crucial. One of the primary requirements is the development of advanced propulsion systems. Current rocket technology relies on chemical propulsion, which is efficient for launching from Earth, but inefficient for long-distance space travel. Innovations in propulsion, such as nuclear thermal propulsion or ion drives, could vastly reduce travel time and increase the feasibility of missions to distant planets like Mars or beyond. Another essential advancement involves life support systems. Traveling to other planets entails not only getting there, but also surviving the journey and the conditions on the destination. This includes creating systems that can efficiently recycle air and water, produce food, and withstand the harsh environment of space. Developing habitats that can protect humans from radiation and extreme temperatures will be necessary. The ability to create self-sustaining environments will play a critical role in long-duration missions. Communication technology also needs improvement to support interplanetary travel. As missions travel further from Earth, the time delay in transmitting signals increases significantly. Currently, sending a message to Mars can take between 3 to 20 minutes, depending on their positions in orbit. Innovations in communication systems would enhance real-time interaction with mission control and improve data transmission rates, which is vital for both operational success and scientific research. Lastly, advancements in robotics and artificial intelligence will be invaluable. Robotic systems could assist in preparation for human missions by conducting preliminary explorations and gathering data. Autonomous robots will become essential for tasks in environments that are inhospitable for humans, making the initial stages of settlement on other planets more manageable. These technologies combined could transform the dream of interplanetary travel into a tangible reality in the coming decades. When we consider exploring other planets or moons, several ethical considerations come to the forefront. One significant aspect revolves around the potential for contamination of these celestial bodies. The introduction of Earth-based microbes could disrupt native ecosystems if they exist, or compromise the integrity of scientific research aimed at understanding the true nature of a remote body. Therefore, planetary protection protocols have been established to ensure that our activities do not irreversibly alter the environments we study. Another ethical dimension relates to the possibility of discovering extraterrestrial life. If we were to find signs of life, our responsibility to protect their environment becomes paramount. This could lead to profound philosophical debates about the rights of non-Earth life forms and how we should engage with them. The ramifications of our actions in such scenarios could extend far beyond scientific discovery, touching upon issues of stewardship and respect for life. Human safety is also a crucial part of the conversation. As we send astronauts to distant worlds, we must prioritize their well-being. Space travel inherently involves risks, hence, ethical considerations include ensuring that missions are planned with the utmost regard for human life. There is a moral obligation to weigh the benefits of exploration against potential hazards faced by explorers. Lastly, the equitable distribution of resources and benefits from space exploration is essential. As nations push for advancements in space technology, it is vital to consider how discoveries and benefits will impact humanity at large. This includes access to potential resources that may be found on other celestial bodies. Ethical exploration demands that we do not fall into the trap of nationalistic competition, but instead work collaboratively, ensuring that the entire planet can share in the wonders and benefits of our ventures into the cosmos. Several groundbreaking telescopes and instruments are on the horizon that promise to transform our comprehension of the universe. Among them, the James Webb Space Telescope stands out as a monumental achievement in astrophysics. Launched at the end of 2021, it is designed to peer deeper into the cosmos than ever before. With its advanced infrared capabilities, the telescope is set to uncover distant galaxies, observe the formation of stars, and explore the atmospheric compositions of exoplanets, providing insights that were previously unreachable. Another significant contender is the European Space Agency's Euclid mission, which aims to explore dark energy and dark matter across the universe. Scheduled to launch in 2023, Euclid will utilize a technique called weak gravitational lensing to map the distribution of matter. This method will allow scientists to study how the universe has evolved over billions of years, filling in gaps in our current understanding of cosmic expansion and the intricate fabric of space-time. Ground-based observatories, too, are on the brink of significant advancements. The extremely large telescope, which is being constructed in Chile, will boast a main mirror measuring 21 meters across, making it the largest optical telescope ever built. This enormous instrument will capture incredibly detailed images of the cosmos, helping researchers unravel the mysteries of black holes, galaxy formation, and the fundamental properties of light and matter. Finally, upcoming missions like the Lunar Gateway and Mars Sample Return are expected to provide direct access to other celestial bodies. These endeavors will allow scientists to study planetary atmospheres, geology, and the potential for life beyond Earth. Each of these innovations represents a step toward a more nuanced understanding of the universe, promising to answer some of humanity's most profound questions about our existence and the cosmos we inhabit. Supernovae play a pivotal role in the cosmic cycle of life and death, significantly influencing the formation of new stars and planetary systems. When a massive star exhausts its nuclear fuel, it can no longer counteract the force of gravity and ultimately collapses under its own weight, leading to a spectacular explosion known as a supernova. This event releases an extraordinary amount of energy and disperses heavy elements throughout the surrounding space, providing the essential building blocks for new stars and planets. The shockwaves generated by a supernova can compress nearby gas and dust clouds, triggering the collapse of these materials under their own gravity. This process, known as star formation, can initiate the birth of new stars from the remnants of the exploded star. The elements produced in the supernova, such as carbon, oxygen, and iron, enrich the interstellar medium, enhancing the chemical complexity of future stellar systems. This means that new stars will be formed from materials that are much more diverse than those of previous generations. Additionally, the intense heat and energy from the supernova explosion can create a series of cascading effects, influencing the dynamics of surrounding molecular clouds. Regions of high density may collapse faster than others, leading to the formation of multiple stars in a cluster rather than a solitary star. These clusters can host star systems with varying characteristics, laying the groundwork for planetary formation around these new stars. The interplay between supernovae and the interstellar medium creates a rich tapestry of cosmic evolution. Each explosion not only signals the end of a star's life, but also leads to the birth of new celestial bodies, ensuring that the universe continues to evolve in complexity and richness. This cycle illustrates how death in the cosmos can pave the way for new beginnings, perpetuating the ongoing story of the universe. Neutron stars serve as a crucial piece of the puzzle in understanding the life cycle of massive stars, particularly at the end of their evolution. When a massive star exhausts its nuclear fuel, it undergoes a spectacular event known as a supernova explosion. This explosion occurs when the core collapses under the force of gravity, leading to a rapid expulsion of the outer layers. What remains is a dense object, often a neutron star, if the remaining core has a mass between approximately 1.4 and 3 solar masses. These extraordinary remnants are composed primarily of neutrons packed into a space no larger than a city. This incredible density means that a sugar cube-sized amount of neutron star material would weigh about the same as a mountain. The existence of neutron stars helps scientists determine the properties of matter under extreme conditions, providing valuable insights into the fundamental forces at play in our universe. Neutron stars are also important for their role as pulsars, which emit beams of radiation that sweep across the sky. When observed from Earth, these beams create a regular pulsing effect, much like a lighthouse. This predictable nature allows astronomers to use pulsars as cosmic clocks, helping to test the laws of physics in ways that were previously impossible. Observations of pulsars can offer key evidence about the interplay between gravity, electromagnetism, and the behavior of matter in extreme states. Furthermore, studying neutron stars aids in our understanding of the beginning and end of massive stars, enriching our grasp of stellar evolution. By examining the data surrounding neutron stars, astronomers can piece together the conditions leading to their formation and the subsequent consequences for the surrounding universe, including the synthesis of heavy elements during supernova events that enrich interstellar space. Thus, neutron stars illuminate not only the life cycles of their progenitors, but also the intricate tapestry of the cosmos itself. Cosmic rays are high-energy particles that travel through space at nearly the speed of light, primarily comprising protons and atomic nuclei. When these energetic particles collide with atoms in the Earth's atmosphere, they produce a cascade of secondary particles and radiation. Studying cosmic rays allows scientists to peek into some of the most violent and energetic processes occurring in the universe, which cannot be reproduced in laboratories on Earth. One of the significant insights provided by cosmic rays is their origin, which often points to extreme astronomical phenomena. For example, supernova explosions, active galactic nuclei, and neutron star collisions are all powerful enough to accelerate particles to incredibly high energies. Moreover, cosmic rays help us understand the conditions of the universe beyond the solar system. As they travel vast distances, they interact with the interstellar medium and magnetic fields, leading to phenomena such as spallation, which alters their composition. This can inform us about the abundance of certain elements in different cosmic environments and reinforce our understanding of cosmic evolution. The study of cosmic rays also brings about practical applications on Earth. Insights gained from these particles have implications for understanding radiation exposure for astronauts on long space missions, and even for aviation. By deciphering the mysteries encoded in cosmic rays, we continue to unravel the fundamental workings of our universe, revealing processes that are otherwise hidden from view. Solar flares are intense bursts of radiation and energy emanating from the sun's surface. When these flares occur, they release a vast amount of electromagnetic energy, which can significantly affect the Earth and our technology. One of the most immediate effects can be seen in the form of beautiful auroras, which are the result of charged particles interacting with our atmosphere. These stunning light displays in places like the polar regions serve as a visual reminder of the sun's energetic influence. However, the effects of solar flares extend well beyond mere aesthetics. They can disrupt communication systems, including radio signals and global positioning system devices, making navigation more challenging for pilots and sailors. With our increasing dependence on technology, even slight disturbances from solar activity can pose significant risks, such as unreliable internet connectivity or distorted television signals. Since solar flares emit a burst of energetic particles, they can also pose a threat to satellites, which operate outside of Earth's protective atmosphere. Moreover, one of the most concerning outcomes of solar flares is the potential for geomagnetic storms. These storms occur when the charged particles released by a solar flare interact with Earth's magnetic field. Such storms can induce electrical currents in power lines, leading to widespread power outages. For instance, a massive geomagnetic storm in 1989 caused the collapse of Quebec's power grid, leaving millions without electricity for several hours. As we become increasingly reliant on technology, understanding the effects of solar flares is crucial for safeguarding our devices and infrastructure. Ongoing research continues to improve our ability to forecast solar activity, giving us the chance to better prepare for and mitigate the impacts of these natural phenomena. The dynamic relationship between solar flares and life on Earth serves as a reminder of how interconnected our existence is with the vast energies of the cosmos. Asteroids and comets are often considered the building blocks of planetary systems, playing critical roles in their formation and evolution. They remain as remnants from the early solar system, providing a tangible connection to the chaotic processes that shape the planets we know today. Asteroids, primarily found in the asteroid belt between Mars and Jupiter, are rocky bodies that reveal much about the ingredients that make up terrestrial planets like Earth. Their composition allows scientists to glean insights into the conditions of the early solar system, including the temperature, pressure, and material availability at that time. Comets, on the other hand, are icy bodies originating from the distant regions of our solar system, particularly the Kuiper belt and the Oort cloud. Their orbits bring them into the inner solar system, where they heat up and create stunning tails. Comets are particularly fascinating because they contain some of the oldest materials from the frozen outskirts of the solar system, preserving clues about the chemical processes that were occurring when the planets first formed. When comets collide with planets, they can deliver critical compounds, including water and organic materials, which may have contributed to the formation of the oceans and the emergence of life on Earth. Throughout the history of planetary development, the impact of asteroids and comets has been profound. Large impacts can drastically reshape a planet's surface and atmosphere, and in some theories, such impacts may have even triggered mass extinctions. The extinction event that wiped out the dinosaurs, for example, is widely attributed to the collision of a massive asteroid with Earth. These celestial bodies are thus not only avenues for understanding our planetary origins, but they also continue to influence the ecosystems of planets like Earth. Understanding asteroids and comets is vital for assessing potential threats to our planet, as well as for future exploration. Missions targeting these bodies not only aim to gather more information about their compositions and characteristics, but also hold the potential for mining resources to support human activity in space. The study of these ancient travelers provides a glimpse into the past while also opening doors to our future in the cosmos. The ultimate fate of the universe is a topic that has fascinated scientists for decades, leading to several compelling theories. One prominent idea is known as the Big Freeze, which predicts that as the universe continues to expand, it will eventually cool down as stars burn out and galaxies drift apart. Over unimaginable spans of time, this could result in a dark, cold universe where nothing much happens, as all energy sources diminish and black holes evaporate. Another theory is the Big Crunch, which suggests that if the universe has enough mass, the gravitational pull could eventually halt its expansion. This would trigger a contraction, pulling everything back together until it collapses into a singularity similar to the state of the universe before the Big Bang. This cyclical view implies that the universe could go through endless cycles of expansion and contraction. Then there is the concept of the Big Rip, which envisions a scenario in which the universe's expansion accelerates uncontrollably due to dark energy. This would eventually tear apart galaxies, stars, planets, and even atomic particles. The prevailing force of expansion could lead to a catastrophic end where the fabric of reality itself unravels. Each of these theories presents a unique perspective on the universe's destiny, influenced by our growing understanding of fundamental forces and cosmic phenomena. Scientists are continually gathering data to refine these concepts, opening up intriguing discussions about not just where we come from, but where we are heading. The mysteries of the universe keep inviting us to explore, and with each discovery, we delve deeper into our cosmic future. The concept of heat death presents a scenario in which the universe ultimately reaches a state of maximum entropy, where all energy is evenly distributed. This process stems from the second law of thermodynamics, which states that in a closed system, entropy tends to increase. Over incredibly vast timescales, stars will burn out, galaxies will drift apart, and matter will become increasingly diluted. As energy resources become exhausted, the universe will resemble a desolate landscape filled with cold, lifeless remnants. All physical processes will effectively cease. In this state, the cosmos will lack the energy gradients needed for any work to occur. Without these gradients, even the most fundamental interactions like chemical reactions or the formation of new celestial bodies will become impossible. The heat death implies a universe where temperatures approach absolute zero. With a uniform distribution of energy, the once vibrant cosmos would be transformed into a dark and stagnant realm, devoid of stars or galaxies, existing for eternity without change. This scenario leaves little room for life as we understand it, leading to a silent cosmic solitude. While this end scenario may seem bleak, it highlights the inevitable march toward disorder prevalent in physical systems. The heat death serves to remind us of the transient nature of existence itself, as the universe drifts further into a stark, energyless eternity. The Big Crunch theory is a fascinating concept in cosmology that proposes a potential fate for our universe. According to this theory, if the density of matter and energy in the universe is high enough, the expansion of the universe, which began with the Big Bang, could eventually halt and reverse. This reversal would lead to a scenario where galaxies begin to fall back toward each other, culminating in a collapse. The universe would contract to an extraordinarily hot and dense state, possibly resulting in a singularity similar to what existed at the beginning of time. There is a variety of evidence to consider regarding this theory. Observations of the universe's expansion have shown that, in the late 20th century, it began to accelerate instead of slow down. This discovery offers a counterpoint to the Big Crunch scenario. The presence of dark energy, a mysterious force believed to permeate space, appears to be driving this acceleration. This suggests that instead of gravitational forces pulling everything back together, the universe's expansion is becoming more pronounced. However, cosmologists continue to study the universe's rate of expansion and its overall density. Measurements indicate that while dark energy dominates the universe's large scale, the total density does not reach the critical threshold needed to sustain the Big Crunch. Future observations and advancements in technology may yield new insights that could either support or refute the Big Crunch hypothesis. The understanding of cosmic fate remains an active area of inquiry, prompting ongoing exploration into the underlying dynamics of our universe. While the current evidence leans against the Big Crunch, it is essential to approach these cosmic questions with an open mind. Our understanding of dark energy is still in its infancy, and the revelations yet to come may alter existing theories, keeping the mystery of the universe alive. The Big Rip theory presents a strikingly different vision for the end of the universe compared to more traditional theories like the Big Freeze or the Big Crunch. At its core, the Big Rip suggests that the very fabric of the universe could eventually tear apart due to the accelerating expansion driven by dark energy. Rather than gradually slowing down or collapsing in on itself, as other theories propose, the Big Rip posits that the expansion of space itself becomes so extreme that it overwhelms all known forces. In this scenario, galaxies would first be pulled apart from one another, stretching further apart as the expansion accelerates. This would be followed by the disintegration of star systems, as gravitational forces are unable to counteract the relentless pull of dark energy. Stars would then become unbound, floating freely throughout their regions of space, while the forces acting on planets could lead to their own unraveling. As the theory extends, it suggests that even atoms and subatomic particles would face destruction, leading to a universal state where all matter disintegrates completely. It is a dramatic conclusion to cosmic evolution, culminating in a universe devoid of meaningful structure, all tied together by the intricate dance of dark energy that propels this expansive tearing. The Big Rip stands out in the cosmic discussion not merely because of its grim implications, but also because it emphasizes the ongoing mysteries surrounding dark energy, which remains one of the most enigmatic components of our universe. How this mysterious force behaves over cosmic timescales is fundamental to determining our universe's fate. Entropy is a fundamental concept in the universe that relates to the degree of disorder within a system. It is central to the second law of thermodynamics, which states that in an isolated system, entropy tends to increase over time. This increase in disorder has significant implications for the future of cosmic processes and structures. As the universe evolves, it expands and cools, leading to various cosmic phenomena. Entropy influences everything from the formation of stars and galaxies to the eventual fate of the universe itself. For instance, when stars burn through their nuclear fuel, they undergo transformations that increase the overall entropy in their environments. Supernovae, or exploding stars, scatter elements and energy throughout space, contributing to the gradual increase of entropy in the cosmos. Over incredibly long timescales, the universe's progression toward higher entropy could imply a colder, more uniform state. This scenario is known as the heat death of the universe, where star formation ceases, galaxies drift apart, and all matter is diluted to such an extent that meaningful interactions become exceedingly rare. The universe would approach a state of maximum entropy, where energy is evenly distributed. Interestingly, while entropy suggests a future of increasing disorder, it is also the driving force behind the complexities we observe today. The beautiful structures of galaxies, stars, and planets have emerged from the gradual balance between order and chaos. Thus, the role of entropy is not just about decline, it serves as a pivotal mechanism that shapes the trajectories of cosmic processes for billions of years. Ancient civilizations viewed the cosmos as a vital and influential component of their world. Their interpretations were deeply intertwined with their cultural practices, religious beliefs, and day-to-day life. For example, the Mesopotamians, who thrived around 4,000 years ago, meticulously tracked celestial movements. They associated planets with their deities, believing these heavenly bodies were directly involved in human affairs, guiding events both mundane and monumental. Similarly, the ancient Egyptians oriented their lives around the stars and the sun. The Great Pyramid of Giza is aligned with incredible precision to the cardinal points and was thought to be a means for the pharaohs to travel to the afterlife among the stars. Their worship of the sun god Ra reflected the significance of solar cycles, which informed agricultural practices, religious festivals, and seasonal changes. In ancient China, astronomical observations were crucial for divination and the court's decision-making processes. The Chinese developed a complex understanding of celestial phenomena, including eclipses and planetary conjunctions. These were seen as omens, indicating the health of the state or the ruler's legitimacy. Their comprehensive records allowed them to create a calendar that was essential for agricultural prosperity and societal organization. The Mayans also exemplified a sophisticated understanding of the cosmos. They created an advanced calendar system based on their observations of celestial bodies, particularly Venus. This knowledge not only regulated agricultural cycles, but also played a critical role in their rituals and governing practices, reinforcing the deep connection between the cosmos and everyday life in ancient cultures. The intertwining of the heavens with human experience reveals how the cosmos has long been a mirror reflecting our very existence. Mythology has played a significant role in how various cultures interpret celestial bodies, intertwining the mysteries of the sky with the tales and beliefs of the people. Across different civilizations, stars, planets, and other astronomical phenomena often became key characters in myths, reflecting the cultural values, fears, and hopes of the society. These stories served as a means to understand the cosmos, assigning meaning and purpose to the movements of celestial bodies in relation to human experiences. In ancient Greece, for instance, constellations were mapped based on the lives of heroes and legends. The constellation Orion represents a hunter, and many Greek myths revolve around his adventures. Similarly, the planets were often associated with gods, such as Mars representing Ares, the god of war. The characteristics of these deities frequently mirrored the qualities of the celestial bodies, providing a way for people to make sense of their surroundings through narrative. In contrast, indigenous cultures around the world have their own distinct astronomical mythologies. For instance, Native American tribes often viewed the stars as ancestral spirits or guides, with constellations woven into their traditions and storytelling. The Milky Way, for example, is seen by some tribes as a river of souls or a pathway for the ancestors, emphasizing the connection between the earth and the heavenly realm. Such interpretations not only shaped their calendars and agricultural practices, but also reinforced cultural identity and community bonds. The influence of mythology extends to modern times, where remnants of these ancient stories can still be found in the names we give celestial phenomena. Many of these mythological interpretations help us explore deeper philosophical questions about existence and our place in the universe. As we observe the night sky, we are reminded that the stars have always been a source of wonder, not just scientifically, but also culturally, inviting us to ponder our connection to the cosmos and to one another. The portrayal of space travel in films and literature has undergone a remarkable evolution, reflecting advancements in technology and shifts in societal attitudes toward exploration. In the early 20th century, works like Edgar Rice Burroughs' A Princess of Mars introduced readers to imaginative concepts of interplanetary travel. These narratives often combined fantasy with adventure, as characters traversed exotic landscapes, highlighting the excitement of the unknown while largely ignoring the scientific feasibility of such journeys. As technology progressed, so did the themes within space narratives. The mid-20th century saw groundbreaking films like Destination Moon, which embraced a more realistic approach to the concept of space travel. This period coincided with the dawn of the space age, fueled by actual achievements such as launching the first artificial satellite and sending humans into orbit. Authors like Arthur C. Clarke began to weave in scientific principles, forecasting plausible technologies and scenarios that would resonate with audiences who could now witness the reality of space exploration. By the late 20th century, representations evolved further with a greater focus on the human experience. Films like Star Wars and Contact captured the complexities of human emotions and social issues against a backdrop of space. Literature began to explore philosophical questions surrounding our place in the universe, influenced by the ongoing discoveries in astronomy and the potential for extraterrestrial life. This era signified a shift from purely adventurous tales to narratives that provoked deeper reflections on humanity's future and ethical dilemmas in space. Today, contemporary portrayals of space travel incorporate cutting-edge science, exploring multidimensional themes such as colonization, artificial intelligence, and the socio-political implications of extraterrestrial contact. Films like The Martian and series such as The Expanse present detailed scientific accuracy alongside gripping human stories, revealing a matured understanding of both the physical and psychological challenges of traveling in space. As our own journeys into the cosmos continue to develop, it is clear that our artistic interpretations will keep pace, reflecting our hopes, fears, and aspirations regarding the universe beyond our home planet. The quest for extraterrestrial intelligence profoundly influences how people view humanity's role in the cosmos. As scientists employ advanced technology and innovative methods to search for signals or signs of life beyond Earth, they spark both curiosity and reflection within society. This ongoing search raises fundamental questions about our uniqueness, our origins, and ultimately our future in the universe. Engagement with the notion of extraterrestrial life can lead to a sense of interconnectedness. Many individuals begin to contemplate not only the possibility of other intelligent beings, but also what it means for our planet and species. The realization that we may not be alone can be both humbling and exhilarating. It invites philosophical discussions about existence, intelligence, and the potential for cooperation or conflict with life forms unlike ourselves. Additionally, the implications of discovering extraterrestrial intelligence could challenge established beliefs and values. For instance, if other civilizations exist, it might prompt us to reevaluate humanity's perceived superiority over nature. It could reduce the sense of isolation, fostering a feeling of being part of a larger cosmic community. Conversely, it may cause anxiety regarding our vulnerability and security if there are advanced civilizations out there with the capability to influence or even threaten our existence. The search for extraterrestrial intelligence is not just a scientific endeavor, it is a cultural phenomenon, intertwining with art, religion, and societal norms. As humanity continues to explore this enormous question, our understanding of ourselves will inevitably evolve. The excitement of possibly making contact with another intelligent species fosters a collective imagination about the universe's vast possibilities and ignites a longing to understand where we truly fit within this grand tapestry of existence. Scientific discoveries about the universe spark profound philosophical discussions that touch on fundamental questions of existence, knowledge, and our place within the cosmos. For instance, the revelations from astronomy, such as the vastness of the universe and the potential for extraterrestrial life, challenge traditional views of humanity's significance. Philosophers ponder whether we are alone in the universe or merely a tiny component of something much grander. Moreover, discoveries such as the Big Bang theory and the concept of an expanding universe provoke inquiries about the origin of everything we know. These questions extend into the realm of metaphysics, pushing thinkers to consider the nature of time and space, and whether the universe had a beginning or exists in an eternal cycle. Such discussions often lead to new interpretations of creation myths and religious narratives, forcing a dialogue between science and spirituality. Science also confronts philosophical issues related to determinism and free will. Quantum mechanics, with its inherent randomness, raises questions about predictability and causality, leading to discussions about whether human actions are predetermined or if there is room for choice in a seemingly deterministic universe. This interplay of scientific understanding and philosophical inquiry enriches both fields, as insights from one can illuminate the other. Finally, as we develop advanced technologies that allow us to explore previously uncharted territories of space, ethical considerations gain prominence. The implications of potentially colonizing other planets or encountering alien life forms require a re-evaluation of our ethical frameworks and responsibilities. Engaging with these scientific breakthroughs not only expands our knowledge, but also deepens our philosophical perspectives, fostering a culture of inquiry that embraces both exploration and reflection. The Fermi Paradox presents a fascinating conundrum in the quest to understand the universe and our potential cosmic neighbors. Named after the physicist Enrico Fermi, it arises from the apparent contradiction between the high probability of extraterrestrial civilizations in the vast cosmos and the conspicuous absence of any evidence for their existence or contact with us. The universe contains billions of galaxies, each with millions or even billions of stars. Many of these stars have planets within their habitable zones, which raises the question, if the conditions for life are so prevalent, where is everyone? This paradox deepens our inquiry, prompting scientists and cosmologists to explore several theories attempting to explain the silence. One possible explanation is that intelligent life is exceedingly rare, suggesting that while life may be common, intelligent civilizations capable of communication or space travel are few and far between. This could be due to various factors, including environmental conditions that inhibit the development of complex life, catastrophic events that wipe out civilizations, or the limitations of natural selection that favor simpler life forms. Another consideration is that advanced civilizations might be choosing not to communicate. They could be observing us from afar, adhering to a principle of non-interference. This idea parallels our own interactions with primitive cultures on Earth, where protecting the integrity of indigenous lifestyles can take precedence over contact. Alternatively, civilizations may be using technologies that we do not yet comprehend, rendering their attempts to communicate undetectable with our current methods. The Fermi Paradox also sparks philosophical discussions about humanity's place in the universe and the profound implications of our isolation. If we are indeed alone, it might call into question the uniqueness of human intelligence and the value of our civilization. Conversely, if we are not alone, the potential for discovering other intelligent life raises thrilling possibilities for collaboration, exchange, and newfound understanding in the grand scheme of the cosmos. The search for extraterrestrial intelligence continues, and each new discovery only deepens the mystery surrounding our existence amidst a seemingly silent universe. The search for signals from alien civilizations has been a fascinating endeavor that combines advanced technology with our unending curiosity about the cosmos. One of the foremost methods employed is called the Search for Extraterrestrial Intelligence, or SETI. Since its inception in the 1960s, SETI has utilized radio telescopes to scan the skies for unusual signals that could indicate the presence of intelligent life. These telescopes pick up a wide range of frequencies, and scientists analyze them for patterns that deviate from natural cosmic noise, hoping they might point to something manufactured. One of the most famous projects within SETI is the use of the Arecibo Observatory in Puerto Rico, which acted as a powerful receiver and transmitter for radio waves. In 1974, researchers transmitted a binary message aimed at the star cluster M13 in hopes of reaching any potential civilizations that might exist there. This message contained fundamental information about humanity and our location, represented in a series of zeros and ones, but the likelihood of a response remains speculative and distant. Modern technology has significantly broadened our ability to search for extraterrestrial signals. With advancements in computer processing power, we can now analyze vast amounts of data more efficiently than ever before. Projects like the Breakthrough Listen initiative utilize powerful telescopes and collect data continuously from the entire sky. This includes monitoring thousands of potential targets at once in the hopes of catching a fleeting signal that may stand out amidst the cosmic background noise. Scientists are also expanding the search beyond just radio waves. Optical SETI programs scan the skies for laser pulses that could be used by advanced civilizations to communicate across vast distances. These multifaceted approaches reflect humanity's deep desire to connect with others in the universe, illustrating not just our technological capabilities, but also our profound longing to discover whether we are alone in this vast cosmos. Sending messages to potential extraterrestrial life presents numerous challenges that stretch across technological, scientific, and even philosophical dimensions. One of the foremost issues is the vastness of space. Distances between stars are incredibly great, often spanning several light years. A message sent from Earth, using current technology, could take years or even decades to reach its destination, depending on how far away the target civilization might be. For instance, a signal aimed at Proxima Centauri, the closest star to our solar system, would take approximately 4 years to arrive. Another significant hurdle is the choice of the message itself. It is difficult to determine the most effective way to communicate across such vast differences. Human languages and symbols are deeply rooted in our cultural context, which may not resonate with an extraterrestrial intelligence. Scientists have considered sending mathematical concepts or scientific fundamentals, such as the laws of physics, which might be universally understood. However, there remains uncertainty about whether such messages would effectively convey meaning or elicit a response from beings with potentially very different forms of cognition and communication. Moreover, the technology used to transmit messages is also a concern. Current methods, such as radio waves, may not be the most efficient or reliable over interstellar distances. These signals can easily be absorbed or distorted by cosmic phenomena such as dust or gas clouds, making the original message difficult to detect or interpret. As we look to the future, advancements in transmission technology could provide better means to convey these messages, but also brings about questions regarding the format and medium used. Finally, there is the philosophical question of whether we should send such messages at all. Some argue that making our presence known may pose risks, as it could attract unwanted attention from potentially hostile civilizations. Others believe that reaching out could foster connections and promote understanding among intelligent life in the universe. As humanity navigates these challenges, the quest to communicate with extraterrestrial life continues, leaving us pondering our place within the cosmos. Radio waves travel through the vacuum of space as electromagnetic radiation. They are part of the electromagnetic spectrum, which also includes visible light, ultraviolet rays, and X-rays. This radiation does not need a medium, such as air or water, to propagate. Instead, radio waves move through the fabric of space itself at the speed of light, which is approximately 300,000 kilometers per second. This remarkable speed allows them to cover vast distances, such as the space between our home planet and distant stars or galaxies. As radio waves journey across these immense distances, they can encounter various obstacles, but they are quite efficient at bypassing many of them. For instance, unlike sound waves, which require a medium to travel through, radio waves can penetrate clouds, dust, and even the upper layers of the Earth's atmosphere. This ability allows astronomers to collect signals from cosmic phenomena that would otherwise be obscured by these barriers, enabling us to gather information about events occurring light years away. The strength of radio waves diminishes with distance due to spreading over a larger area. This phenomenon is known as the inverse square law, which means as waves travel farther from their source, they spread out. Therefore, the intensity of the signal decreases, making detection more challenging. However, advancements in technology, such as sensitive radio telescopes and amplifying devices, have improved our capabilities to capture these faint signals, allowing us to explore the universe in ways previously thought impossible. Intriguingly, radio waves can also be affected by celestial events. For example, when they encounter charged particles in the solar wind, they can undergo scattering, which slightly alters their trajectory. Such interactions make radio astronomers continually refine their methods to isolate signals from space, ensuring accurate data collection that fuels our understanding of the cosmos. Communicating with potential extraterrestrial civilizations brings forth a multitude of ethical considerations that challenge our understanding of responsibility and the implications of contact. One of the primary concerns revolves around the potential risk of cultural contamination. If we were to establish communication with an alien civilization, there is a fear that our own culture, beliefs, and values could impose themselves on theirs, possibly erasing the unique identity that they have developed over countless generations. Another significant ethical issue is the assumption of equality in intelligence and understanding. When we attempt to initiate contact, we must consider that the extraterrestrial beings may possess vastly different cognitive structures, ethical systems, and ways of interpreting reality. This disparity poses challenges in communication, as we might project our own worldview onto them, potentially leading to misunderstandings. The responsibility lies in developing a communication approach that is respectful and genuinely seeks to understand without domination. There is also the question of whether we have the right to communicate at all. Some theorists argue that by reaching out, we could inadvertently expose these civilizations to dangers they are unprepared for, such as exploitation by more advanced species, including ourselves. This puts into question whether it is ethical to take the initiative in contact when we cannot ensure the safety of potentially vulnerable, less advanced societies. Moreover, there is the issue of what messages we choose to send out into the cosmos. The content of such communications could reflect our values, intentions, and even our competitive nature. As humanity, we must consider whether we want to represent ourselves as peaceful explorers or as potential conquerors. This decision-making process becomes a heavy burden of responsibility that reflects on not only our species, but also the legacy we wish to leave in the universe. Balancing the pursuit of knowledge with respect for other intelligent life forms requires careful thought and consideration. The evolution of astronomical technology has profoundly transformed our understanding of the universe. Just a few decades ago, our observations were largely limited to visible light. Telescopes like the ones used by early astronomers could only capture the faint light from stars and planets, and this restricted our comprehension of celestial phenomena. However, with advances in technology, we now have access to a broader spectrum of electromagnetic radiation, including radio waves, infrared, ultraviolet, X-rays, and gamma rays. This has allowed scientists to gather information about the universe that was once invisible to us. One remarkable example is the Hubble Space Telescope, launched in 1990. This powerful instrument orbits above the Earth's atmosphere, which limits ground-based telescopes. The Hubble has captured stunning images and provided data that has expanded our knowledge of distant galaxies, nebulae, and even exoplanets. Its observations have led to groundbreaking discoveries, such as the discovery of dark energy, which is driving the accelerated expansion of the universe. Armed with this knowledge, astronomers now have a better understanding of the cosmos's structure and evolution, revealing layers of complexity that were previously hidden. Similarly, the development of radio astronomy has opened new windows to explore celestial phenomena. By detecting radio waves emitted by objects in space, astronomers discovered pulsars, the remnants of supernova explosions, and the cosmic microwave background radiation. This last discovery has played a crucial role in shaping our understanding of the universe's beginnings and supports the Big Bang theory, revealing the conditions of the early cosmos. Advanced radio arrays and observatories, like the Very Large Array in New Mexico, have enabled scientists to probe the universe much deeper than ever before. More recently, the advent of gravitational wave detectors has added another dimension to our understanding. The first detection in 2015 confirmed the existence of ripples in space-time caused by massive merging objects, such as black holes and neutron stars, providing valuable insights into their nature and the processes that govern them. With each technological advancement, our capacity to explore the universe grows, leading us to exciting discoveries and a deeper appreciation of the cosmos and our place within it. Astrophysics serves as a bridge between the fundamental laws of physics and the vast universe, providing the tools and methodologies needed to unravel cosmic mysteries. By applying principles from physics and mathematics, astrophysicists can explain phenomena ranging from the life cycles of stars to the behavior of galaxies. This discipline enables scientists to create models, formulate theories, and make predictions about celestial objects and events that are often millions or even billions of light years away. One of the critical roles of astrophysics is its ability to analyze light from distant stars and galaxies, allowing scientists to understand their composition, temperature, and movement. The spectrum of light reveals intricate details about celestial bodies. For instance, the absorption lines in a star's spectrum can tell us the elements present in its atmosphere, while the redshift can indicate how fast it is moving away from us, giving insight into the expansion of the universe. Astrophysical research also involves the study of cosmic phenomena such as black holes and neutron stars. These dense remnants of stellar evolution challenge our understanding of physics, especially under extreme conditions. By investigating these objects, astrophysicists push the boundaries of established scientific theories, exploring concepts such as general relativity and quantum mechanics in contexts that are not reproducible on Earth. Furthermore, astrophysics has profound implications for our understanding of fundamental questions about the universe and our place within it. It examines not only the birth and death of stars, but also the structure of space-time itself and the evolution of galaxies. As we decode cosmic mysteries, we invite a deeper appreciation of the cosmos, highlighting the interconnectedness of all matter and energy in the universe. Simulations provide scientists with invaluable tools for visualizing the complex processes involved in galaxy formation. By using powerful computers and sophisticated algorithms, researchers can create detailed models that mimic the behaviors of gas, dust, and dark matter across vast cosmic distances. These simulations allow scientists to observe how galaxies might evolve over billions of years as they form from swirling clouds of gas and merge with other galaxies. One of the key benefits of simulations is their ability to include various physical phenomena, such as gravity, pressure, and thermal dynamics. These factors play a crucial role in galaxy formation, influencing how matter coalesces and gives rise to stars and other structures. By manipulating these variables, scientists can explore different scenarios, helping to identify the conditions that lead to the formation of spiral galaxies, elliptical galaxies, and irregular galaxies. Additionally, visualizations from simulations can highlight the role of dark matter, which is not directly observable, but is essential in understanding the universe. Dark matter acts as a scaffold for visible matter, dictating how galaxies and clusters of galaxies develop over time. These simulations shine a light on the distribution of dark matter, offering insights into how it interacts with regular matter and affects galaxy formation. These powerful visual tools help demystify the universe's history and evolution, enriching our understanding of how galaxies are born, grow, and interact. As scientists study the results of these simulations, they can compare them against observational data from telescopes, refining their models and advancing our knowledge of the cosmos. This interplay between simulation and observation not only enhances our grasp of galaxy formation, but also illustrates the profound complexities of our universe. The Hubble constant plays a crucial role in understanding the expansion of the universe. It is a value that quantifies the rate at which galaxies are moving away from us. Essentially, the greater the distance between us and a galaxy, the faster it appears to be receding. Edwin Hubble first noticed this relationship in the early 20th century, leading to the realization that the universe is not static, but rather dynamic and expanding. This constant helps astronomers determine the distance to galaxies based on their redshift, the phenomenon where light from an object shifts toward the red end of the spectrum as it moves away. By measuring how much the light has shifted, scientists can calculate how far away that object is, and by extension how fast it is moving. The Hubble constant is essential in this calculation because it provides the proportionality factor needed to relate velocity and distance. Accurate measurements of the Hubble constant are vital for understanding not only how fast the universe is expanding, but also its age and size. Current estimates suggest that the universe is approximately 13.8 billion years old. However, discrepancies exist in different methods of measurement, leading to discussions around what is referred to as the Hubble tension, where various methods yield different values for this constant. Ultimately, the importance of the Hubble constant extends beyond mere distance calculations. It leads to deeper insights into the nature of the cosmos, including the effects of dark energy, an enigmatic force driving the accelerated expansion of the universe. Understanding this constant enhances our comprehension of cosmic history and the fundamental mechanics governing our universe. Cosmic maps are essential tools in unraveling the large-scale structure of the universe. By charting the distribution of galaxies, clusters, and cosmic voids, these maps provide a three-dimensional representation of the cosmos. The data collected from various telescopes and surveys reveal how matter is organized on a grand scale, enabling scientists to identify patterns and structures that stretch across billions of light-years. One of the most significant insights gained from cosmic mapping is the realization that the universe is not uniformly distributed. Instead, it reveals a complex web-like structure known as the cosmic web, where galaxies are interconnected by filaments of dark matter. These filaments surround vast voids where few galaxies are found. Understanding this structure is crucial because it influences gravitational forces, which in turn affect galaxy formation and evolution. Moreover, cosmic maps aid in testing theories of cosmic evolution. For example, researchers can compare observations with simulations that model how structures form over time under the influence of gravity and dark energy. Discrepancies between the two allow scientists to fine-tune their understanding of the physical laws governing the universe. As technology improves, more detailed maps will continue to emerge, providing an even clearer insight into the intricate tapestry of the cosmos. These maps not only enhance our grasp of cosmology, but also raise intriguing questions about the fundamental nature of reality, including the distribution and role of dark matter and dark energy in shaping the universe. Light from distant stars serves as a remarkable time capsule, revealing the universe's past in ways that spark the curiosity of astronomers and scientists alike. When we observe a star, we are not merely looking at its present condition. Rather, we are seeing light that may have traveled millions or even billions of years to reach us. This delay allows us to glimpse the universe not as it is today, but as it was when the light first began its journey. The spectrum of light emitted by stars contains crucial information about their composition, temperature, and motion. When astronomers analyze this light, they can identify specific spectral lines that indicate the presence of various elements and compounds. For example, the presence of hydrogen and helium in distant stars can inform us about the conditions prevalent in the early universe, shortly after the Big Bang. By examining these elements, scientists can piece together the chemical evolution of the cosmos. Moreover, the redshift of light from distant galaxies provides insight into the universe's expansion. When light waves stretch as they travel through space, they shift toward the red end of the spectrum. This phenomenon allows astronomers to determine how far away the galaxy is and how fast it is moving away from us. Consequently, Redshift data leads to a better understanding of the rate at which the universe is expanding, revealing the dynamics of cosmic history. As we gaze into the night sky, each sparkle represents a story, shedding light not just on individual celestial objects, but also on the intricate narrative of our universe's evolution. By studying these distant luminaries, we gain invaluable insight into the formation of galaxies, the life cycle of stars, and the expansive tapestry of the cosmos itself. Redshift is a key concept in understanding the expansion of the universe. When we observe light from distant galaxies, we find that it is often shifted toward longer wavelengths, which we refer to as redshift. This shift occurs because the universe is expanding. As galaxies move away from us, the light they emit stretches, much like a stretched rubber band. The greater the distance between us and a galaxy, the more its light is redshifted. This phenomenon was first identified by Edwin Hubble in the early 20th century. He discovered that galaxies farther away from us not only exhibit more redshift, but also appear to recede faster than those that are closer. This observation led to the formulation of Hubble's law, which establishes a direct correlation between a galaxy's distance and its redshift, reinforcing the idea that the universe is uniformly expanding. The implications of redshift extend beyond mere observation. They provide critical evidence supporting the Big Bang theory. By analyzing the redshift of light from various celestial objects, astronomers can calculate how fast the universe has been expanding since its inception approximately 13.8 billion years ago. This expansion implies that at one point in time, all matter and energy were concentrated into an incredibly small and dense state, leading to the universe's subsequent growth and the formation of galaxies. Moreover, current observations of redshift have revealed unexpected insights, such as the acceleration of the universe's expansion. This has led to the hypothesis of dark energy, a mysterious force driving galaxies further apart at an increasing rate. The study of redshift, therefore, not only helps us understand how the universe is expanding, but also raises profound questions about the fundamental nature of reality. Different wavelengths of light unlock a treasure trove of information about cosmic phenomena. Our eyes can only perceive a tiny portion of the electromagnetic spectrum, known as visible light, but the universe emits a broad range of electromagnetic radiation. This spectrum includes ultraviolet, infrared, X-rays, and radio waves, each revealing unique aspects of celestial objects and events. For instance, ultraviolet light is emitted by incredibly hot stars and energetic phenomena. By studying this wavelength, astronomers can determine the temperature and composition of stars, as well as identify regions of star formation. On the other end of the spectrum, infrared light is useful for observing cooler objects, such as planets or dust clouds, allowing scientists to peer through dense cosmic dust that obscures visible light. X-rays come from the most energetic environments, such as supernova remnants and the vicinity of black holes. Analyzing X-ray emissions helps astronomers understand the extreme conditions present in these regions, giving insights into the life cycles of stars and the behavior of matter in the presence of strong gravitational fields. Radio waves, being even longer in wavelength, reveal the presence of cosmic structures like pulsars and galaxies, enabling the mapping of large-scale structures in the universe. Each wavelength provides a different perspective on the cosmos, offering clues to the composition, temperature, and dynamics of celestial bodies. When combined, these various data points create a more complete picture of our universe, enhancing our understanding of its intricate nature and the processes that govern it. Observing the universe through visible light presents various limitations that can significantly hinder our understanding of cosmic phenomena. Firstly, visible light makes up only a small fraction of the electromagnetic spectrum. While we can see a range of colors from violet to red, other important wavelengths, such as ultraviolet, X-rays, radio waves, and infrared, are invisible to the human eye. This narrow band restricts our view of the universe, preventing us from detecting emissions and signals from many celestial objects and events that occur outside this spectrum. Furthermore, atmospheric interference poses substantial challenges when observing from Earth. The atmosphere absorbs and scatters visible light, causing distortions and limiting clarity. This is why many observatories are located at high altitudes or on remote islands, where the air is thinner and light can penetrate more easily. Some astronomical phenomena may only be observed through their emissions in other wavelengths, which are often absorbed or obscured by atmospheric effects, further complicating our ability to study them effectively through visible light alone. Additionally, objects that are very distant or inherently faint can elude detection when only visible light is taken into account. For example, distant galaxies emitting mostly infrared radiation or black holes that release X-rays are largely invisible to our naked eye. Without the help of specialized instruments that can detect these other wavelengths, we miss out on crucial information regarding their properties and the processes occurring within them. The universe is full of dynamic and complex structures that can emit across various parts of the electromagnetic spectrum. By limiting ourselves to just visible light, we risk acquiring an incomplete and skewed perspective of the cosmos. Employing a multi-wavelength approach to astronomy allows scientists to paint a more comprehensive picture, revealing the myriad processes that govern the universe beyond what is visible. Spectroscopy has transformed our comprehension of celestial bodies by allowing scientists to analyze the light emitted, absorbed, or reflected by these objects. When light from a star or planet passes through a prism or a diffraction grating, it separates into its component colors, revealing a spectrum. This spectrum contains vital information about the chemical elements present in the celestial body, as each element produces a unique set of spectral lines. These lines act like fingerprints, enabling astronomers to identify and quantify the elements even from vast distances. One of the key advancements brought by spectroscopy is its ability to provide insights into the temperature, density, and motion of celestial objects. By analyzing the Doppler shift of spectral lines, astronomers can determine if an object is moving towards or away from us, offering clues about the expansion of the universe and the dynamics of galaxies. This technique has enabled the discovery of exoplanets and has paved the way for understanding stellar evolution, supernova mechanisms, and the development of galaxies. Moreover, spectroscopy has made it possible to study the atmospheres of planets and moons, revealing not just their chemical composition, but also clues about potential habitability. For instance, the detection of water vapor, methane, or carbon dioxide in the atmosphere can indicate the presence of processes that might support life, both in our solar system and beyond. As technology advances, telescopes equipped with spectroscopic instruments are continuously improving our ability to analyze distant worlds. The impact of spectroscopy extends far beyond mere identification of chemical elements. Its application has reshaped our view of the cosmos, allowing for more profound insights into the fundamental processes that govern the universe. Engaging with this powerful tool offers a glimpse into the intricate fabric woven throughout space, where chemical interactions tell the history and nature of celestial phenomena. Astrobiology serves as a vital link between astronomy and biology, exploring the possibilities of life beyond our planet, while understanding the fundamental characteristics of life as we know it. This interdisciplinary field combines principles from both disciplines, addressing questions about where and how life might exist in the universe. Astrobiologists examine extreme environments on Earth, such as deep-sea hydrothermal vents and acidic hot springs, to gain insights into how life could potentially survive on other celestial bodies. By studying organisms that thrive in harsh conditions, scientists can start to imagine the kind of life forms that might develop on planets with extreme temperatures, pressures, or chemical compositions. For instance, life on Mars may require adaptations quite different from those found here on Earth. The discovery of extremophiles, organisms that can endure environments previously thought to be uninhabitable, broadens our understanding of life's potential variations. These findings hint that if life could emerge in hostile environments on our own planet, it could also arise elsewhere. Furthermore, astrobiology relies heavily on astronomical observations to identify potentially habitable exoplanets, or planets outside our solar system. Through the use of advanced telescopes, scientists analyze these distant worlds for indicators such as the presence of water, atmospheric composition, and surface conditions. These data guide researchers in forming hypotheses about what kinds of biological systems may exist or have existed in those environments. Ultimately, astrobiology enriches our understanding of both the universe and the nature of life itself. It encourages a holistic approach that allows scientists to use astronomical discoveries to inform biological theories, thus bridging the gap between the cosmos and the origins, evolution, and potential futures of life on Earth and beyond. This collaboration between disciplines not only fuels scientific curiosity, but also enhances our appreciation of our own existence in the grand tapestry of the universe. Throughout our solar system, several intriguing environments have emerged as the most promising candidates for harboring life. One of the most discussed locations is Europa, one of Jupiter's moons. Beneath its thick layer of ice lies a vast ocean of liquid water, which is essential for life as we know it. Scientists believe that this ocean could contain the necessary chemical ingredients and the energy sources required for life, similar to hydrothermal vents found deep in Earth's oceans. Another exciting locale is Enceladus, a moon of Saturn. It has surprised researchers with its active plumes that eject water vapor and organic compounds into space. These geysers suggest that there is also a subsurface ocean, along with potential energy sources such as hydrothermal activity on the ocean floor. The combination of water, essential nutrients, and energy could create a suitable environment for life to thrive. Mars remains a focus of exploration as well. Evidence from past missions indicates that liquid water once flowed on its surface, and there are signs that it may still exist in subsurface reservoirs. The discovery of seasonal dark streaks on Mars, called recurring slope lineae, hints at the presence of briny water, which poses the possibility for microbial life to persist in this harsh climate. Ongoing research and missions continue to seek evidence of ancient or even current life on this enigmatic planet. Lastly, Titan, Saturn's largest moon, presents an entirely different set of conditions. Unlike Earth, Titan is known for its lakes and rivers of liquid methane and ethane. While this environment is extremely cold, scientists speculate that life could exist in such exotic conditions, utilizing biochemistries unlike those on Earth. This range of environments showcases the diversity of conditions that may allow life to exist beyond our planet. Researchers assess the habitability of exoplanets through a combination of environmental factors, chemical compositions, and observational techniques. The process begins with the identification of planets located within a star's habitable zone, a region where temperatures might allow for liquid water to exist on the surface. This zone varies depending on the star's luminosity, and maintaining an appropriate distance is crucial to ensuring that any surface water does not freeze or vaporize, making this one of the initial criteria for potential habitability. Beyond temperature considerations, scientists analyze the planetary atmosphere. A breathable atmosphere is essential for supporting life as we know it. Researchers look for gases such as oxygen and methane, which can indicate biological processes. Spectroscopy, a technique that studies how light interacts with matter, is often employed to identify these gases as the planet's light spectrum changes when it passes in front of its host star. The presence of a thick atmospheric layer can also create pressure conditions suitable for liquid water, another vital ingredient for life. Moreover, the planet's size and mass are pivotal in determining its potential to retain an atmosphere. Terrestrial planets, having solid surfaces, are considered more favorable for habitability compared to gas giants. The geophysical properties, including geological activity, influence the planet's capacity to cycle nutrients and support potential ecosystems. Scientists examine geological markers through indirect measurements, looking for characteristics that might suggest past or present tectonic activity or volcanic processes. Finally, models of climate systems are developed based on the available data, providing insights into how these planets might retain heat and manage energy from their stars. Considering all these factors, researchers combine data from telescopes with simulations to paint a comprehensive picture of exoplanets, ultimately guiding our understanding of their potential to harbor life. This meticulous evaluation showcases human ingenuity and curiosity as we strive to understand the universe beyond our own planet. Extremophilic organisms, those that thrive in environments once thought to be uninhabitable, are a remarkable key to understanding the potential for life in extreme conditions. These resilient creatures can be found in acidic hot springs, deep ocean vents, and even frozen tundras, showcasing life's extraordinary ability to adapt. Their existence expands the boundaries of how we define habitable conditions, prompting scientists to reconsider where life might exist beyond Earth. The study of extremophiles reveals not just their survival strategies, but also invaluable biochemical processes. For instance, certain bacteria found near hydrothermal vents utilize chemosynthesis, converting inorganic compounds into energy without sunlight. This process highlights an alternative form of life that could potentially thrive on other celestial bodies like icy moons or planets that lack solar energy. Thus, extremophiles push the limits of our imagination about where and how life can exist. Furthermore, these organisms provide insights into early Earth conditions. Understanding how extremophiles survived during times when our planet experienced extreme temperatures and toxic environments offers clues about the origins of life itself. Researchers study these organisms to uncover the resilience and adaptations that enabled life to flourish on Earth, even in its most hostile epochs. As we explore environments like Mars and the icy surfaces of Europa, extremophiles serve as models for potential extraterrestrial life forms. They encourage scientists to investigate not only the extremes of temperature and pressure, but also the diversity of chemical compositions that could support life. Thus, extremophilic organisms not only deepen our comprehension of biology, but also shape our quest to find life beyond our planet. Microbial life forms are often unseen heroes of planetary ecosystems, playing crucial roles that sustain life as we know it. These microscopic organisms include bacteria, archaea, fungi, and protists, and they are found in nearly every habitat on Earth, from the depths of oceans to the highest mountain peaks. They contribute to essential processes such as nutrient cycling, decomposition, and energy production, forming the bedrock of food webs and supporting a vast array of larger life forms. One of the most critical contributions of microbes is their role in nutrient cycling. For example, nitrogen-fixing bacteria convert atmospheric nitrogen into forms that plants can use, which is fundamental for plant growth. Similarly, microbes break down organic matter, recycling nutrients back into the ecosystem. Without these processes, ecosystems would stagnate and life would struggle to thrive. Additionally, certain microbes play important roles in carbon cycling. Some algae and cyanobacteria, through photosynthesis, capture carbon dioxide, releasing oxygen as a byproduct and facilitating a breathable atmosphere for many organisms. Beyond Earth, the study of extremophiles, microbes that thrive in extreme conditions, opens intriguing possibilities for life on other planets or moons. For instance, some bacteria survive in harsh environments like acid lakes, icy terrains, or high radiation areas, suggesting that microbial life could exist on celestial bodies with similar harsh conditions. The discovery of these resilient organisms prompts a re-evaluation of what conditions are necessary for life and where we might find it beyond our own planet. Furthermore, the techniques used to study these life forms are paving the way for future exploratory missions. For instance, investigators analyze samples from Martian soil or the icy subsurface oceans of Europa, looking for signatures of microbial life or its byproducts. Life's resilience on Earth hints that microbial communities could potentially flourish in environments we have yet to fully explore, expanding our understanding of life's possibilities in the cosmos. Different cultures throughout history have grappled with the concept of the vastness of space, weaving their understanding into the fabric of their beliefs, stories, and scientific inquiries. Many indigenous cultures, for instance, have long observed the stars and celestial phenomena, interpreting them through the lens of their mythology and spirituality. The night sky served not just as a natural wonder, but also as a source of guidance, inspiration, and identity. In ancient civilizations like those of Mesopotamia and Egypt, astronomical observations were essential for agriculture, navigation, and developing calendars. The Mesopotamians had a deep understanding of celestial movements and developed astrolabes to track the positions of celestial bodies. They attributed significance to constellations, creating elaborate myths that depicted the relationships between the gods and the cosmos. Meanwhile, the Egyptians associated the stars with their gods and used the stars to align their pyramids and temples precisely. As we move through time, cultures such as the ancient Greeks offered philosophical interpretations, discussing the nature of the universe in terms of order and chaos. Figures like Ptolemy introduced the geocentric model, while later thinkers like Copernicus revolutionized this perspective by proposing a heliocentric view, fundamentally altering humanity's understanding of its place in the cosmos. The Renaissance marked a pivotal moment, where advances in science and technology allowed for a more empirical approach to understanding space. In contemporary society, as space exploration progresses, cultures continue to redefine their relationship with the universe. Global initiatives and advancements in astrophysics encourage collaboration and provoke fresh dialogues about existence and humanity's role in the grand tapestry of the cosmos. Today, the vastness of space serves as both a scientific frontier and a profound source of curiosity, prompting people to seek not only understanding, but also connection to something far greater than themselves. The exploration of space profoundly influences humanity's psychological landscape in various ways. It cultivates a sense of wonder and curiosity, inspiring individuals to look beyond their immediate surroundings and contemplate the vast universe that lies beyond Earth. This exploration encourages profound philosophical questions about our place in the cosmos and our responsibility towards one another and our planet. The questions surrounding existence and the search for extraterrestrial life prompt people to reflect on their beliefs, values, and the shared nature of human experience. Furthermore, the achievements in space exploration contribute significantly to a collective identity. Nations and communities unite in the pursuit of knowledge, instilling pride through technological advancements and cooperative endeavors. The success of missions, such as landing on the Moon or sending rovers to Mars, fosters a shared sense of achievement that transcends borders, promoting diplomacy and collaboration among diverse cultures. This spirit of exploration can lead to increased motivation and a sense of purpose for future generations, encouraging careers in science, technology, engineering, and mathematics. Furthermore, the achievements in space exploration contribute significantly to a collective identity. Nations and communities unite in the pursuit of knowledge, instilling pride through technological advancements and cooperative endeavors. The success of missions, such as landing on the Moon or sending rovers to Mars, fosters a shared sense of achievement that transcends borders, promoting diplomacy and collaboration among diverse cultures. This spirit of exploration can lead to increased motivation and a sense of purpose for future generations, encouraging careers in science, technology, engineering, and mathematics. On a more personal level, individuals often feel a mix of emotions when they contemplate space. The concept of humanity's fragility in the face of the universe can evoke feelings of both insignificance and awe. The famous Earthrise photograph, taken during the Apollo mission, serves as a powerful reminder of our planet's vulnerability and beauty, instilling a sense of responsibility to protect our home. This emotional connection can motivate people to engage more actively in efforts to address global challenges such as climate change, inequality, and global health. As humanity continues its journey into the cosmos, psychological impacts will likely evolve. Future space missions and advancements, such as the potential colonization of other planets, will bring new challenges and uncertainties. These experiences may shape our mental frameworks, influencing how we perceive risks, embrace innovation, and relate to one another in an ever-expanding universe, reminding us that the exploration of space is not only about the stars, but also about understanding ourselves. Space exploration has ignited a passion for science, technology, engineering, and mathematics, commonly known as STEM, inspiring countless individuals to pursue these fields. The excitement generated by missions to distant planets, the discovery of new celestial phenomena, and the sheer spectacle of human ingenuity soaring into space captivates the imaginations of young minds. Schools and educational institutions often leverage the allure of space programs to enhance their curricula, implementing hands-on activities such as rocket building, robotics, and astronomy workshops. Programs such as the National Aeronautics and Space Administration's various outreach initiatives encourage students to engage directly with scientific concepts. These initiatives connect classrooms to cutting-edge research and technology by providing resources like interactive lesson plans, online lectures, and opportunities to collaborate with scientists and engineers. As a result, students become more enthusiastic about science and its applications, seeing firsthand the real-world implications of what they learn. Moreover, major space events, such as launches, landings, and discoveries, capture national attention and spark public interest. This broader cultural enthusiasm translates into increased enrollment in STEM education programs. Many students express a desire to contribute to ongoing exploration efforts, aspiring to become engineers, scientists, or researchers. The rise of satellite technology and space entrepreneurship has further broadened career pathways, reinforcing the idea that STEM fields can lead to extraordinary opportunities. The impact of space exploration on education is evident not only in formal schooling, but also in extracurricular and community programs. Libraries, museums, and community centers organize lectures, science fairs, and astronomy nights, making science accessible and relatable. By weaving the excitement of space exploration into educational pursuits, society fosters a new generation eager to understand the universe, armed with the knowledge and skills to tackle future challenges and drive innovations. Numerous figures have made significant contributions to the conversation surrounding space exploration. One of the most notable is Carl Sagan, an astronomer and science communicator. Through his work on the television series Cosmos, Sagan popularized complex scientific concepts and inspired countless individuals to look toward the stars. His advocacy for space missions, including the Golden Record sent aboard Voyager probes, highlights humanity's desire to communicate with potential extraterrestrial life. Another pivotal figure is Neil Armstrong, who became a symbol of human achievement when he took the first steps on the lunar surface in 1969. His famous words not only captured a historical moment, but also encapsulated the spirit of exploration. Armstrong's journey emphasized the importance of international collaboration, innovation, and courage in venturing into the unknown. The work of Elon Musk has also transformed current narratives in space exploration. Through his company SpaceX, he has aimed to make space travel more accessible and affordable. Musk's ambitious visions, such as colonizing Mars and the development of reusable rocket technology, challenge traditional approaches to space travel. His determination to push the boundaries contrasts with earlier models, inspiring a new generation to dream of life beyond Earth. These individuals represent a diverse array of perspectives and motivations. From the scientific advocacy of Carl Sagan to the groundbreaking achievements of Neil Armstrong and the entrepreneurial spirit of Elon Musk, each has played a crucial role in shaping our understanding and aspirations concerning the cosmos. Their contributions illustrate how the human drive to explore space evolves and how it continues to inspire future generations. The international space community collaborates extensively to tackle cosmic challenges through a combination of shared research, joint missions, and collective problem-solving efforts. Countries and organizations recognize that many of the issues they face, such as asteroids potentially threatening Earth or the complexities of climate change observed from space, require a united front and a pooling of resources. This collaboration fosters a robust exchange of knowledge and technology, ensuring that diverse expertise can be leveraged to address specific challenges. Organizations like the United Nations Office for Outer Space Affairs facilitate international dialogues, guiding discussions on space sustainability and safety. These platforms encourage nations to share their findings and strategies for monitoring near-Earth objects, improving early warning systems for potential hazards. By uniting under frameworks such as the Outer Space Treaty, Countries affirm their commitment to peaceful exploration and the responsible use of space, which promotes stability in international relations and encourages cooperative efforts in research. Joint missions exemplify this spirit of collaboration. The International Space Station serves as a shining example of what can be achieved when nations work together. It is a microcosm of international scientific research where astronauts from different countries conduct experiments that benefit all humanity. Through these coordinated efforts, astronauts learn to operate in an environment where they rely on one another, fostering teamwork that extends beyond mere scientific pursuits into areas of shared humanity. Furthermore, the European Space Agency, NASA, and other space agencies often collaborate on a variety of projects, including satellite launches and scientific research. This pooling of resources maximizes the potential for significant discoveries, enabling advancements in understanding the universe that might not be possible for individual nations acting alone. Such partnerships ultimately help shape a future in space that is inclusive, safe, and beneficial for all of humankind. Several groundbreaking technologies are currently being developed to enhance our capabilities in space exploration. One of the most exciting advancements is the development of reusable rocket systems. Companies like SpaceX have revolutionized space travel by creating rockets that can return to Earth and be launched multiple times. This not only significantly reduces the cost of access to space, but also paves the way for more frequent missions to places like the Moon and Mars. Another remarkable innovation is ion propulsion systems. Unlike traditional chemical rockets, ion thrusters use electric fields to accelerate ions, producing a much more efficient and gradual thrust. This technology enables spacecraft to travel longer distances with less fuel, making it ideal for prolonged missions to distant planets or asteroids. NASA's Dawn spacecraft, which explored the asteroid belt, utilized this kind of propulsion, showcasing the potential for deep space exploration. Artificial intelligence is also playing a crucial role in the future of space exploration. With the immense distances and complexities of space missions, autonomous systems are being designed to help spacecraft make real-time decisions. This includes navigation, hazard detection, and even conducting experiments without waiting for commands from Earth. This technology is especially vital for missions to remote locations, where communication delays can hinder timely responses. Lastly, the push towards sustainable space travel is leading to the development of in-situ resource utilization technologies. This includes the ability to extract water from lunar or Martian soil and convert it into breathable oxygen or rocket fuel. By harnessing local resources, space agencies aim to support long-term human presence beyond Earth, which is essential for missions that could last several years. These innovations collectively represent a new frontier in our quest to explore the cosmos. Three-dimensional printing, along with advanced manufacturing technologies, has transformed the way space mission equipment is designed, produced, and deployed. This remarkable shift allows for the creation of complex components that were once impossible or prohibitively costly to manufacture using traditional methods. By using digital files, spacecraft manufacturers can produce parts on demand, reducing the need for extensive inventories and expensive shipping. One of the most significant benefits of three-dimensional printing is its ability to reduce weight. Components can be designed with a focus on minimalism, using only the material necessary for strength and function. Lighter equipment leads to lower launch costs, as every kilogram counts when sending payloads into space. Furthermore, it allows engineers to think outside conventional designs, crafting geometries that optimize both performance and efficiency. These technologies also enable rapid prototyping, which accelerates the development of new equipment. Engineers can test designs in a matter of days instead of the weeks or months required by traditional techniques. This fast-paced innovation helps missions adapt and evolve to meet new challenges or incorporate cutting-edge technologies, ensuring that exploration remains at the forefront of scientific discovery. Additionally, three-dimensional printing is proving invaluable for long-duration missions, such as those to Mars. Astronauts could potentially produce replacement parts, or even assemble new tools directly in space, minimizing reliance on resupply missions from Earth. This self-sufficiency is crucial for exploring distant realms of our solar system, where the logistics of transporting equipment and parts can be dauntingly complex. As these technologies continue to advance, they promise to further revolutionize our capabilities beyond our planet. Artificial intelligence is revolutionizing the field of astronomical research by significantly enhancing the efficiency of data analysis. With the vast amounts of data generated by modern telescopes and observational instruments, traditional methods of analysis can be slow and labor-intensive. Artificial intelligence algorithms can quickly sift through this data, identifying patterns and anomalies that might go unnoticed by human researchers. This capability accelerates the process of data interpretation and allows scientists to focus on the most promising discoveries. One of the most notable applications of artificial intelligence in astronomy is its role in classification tasks. For instance, machine learning models trained on large datasets can be employed to classify celestial objects such as galaxies, stars, and exoplanets based on their unique characteristics. These models can analyze thousands of images or spectra in a fraction of the time it would take a human, drastically improving the pace at which new findings can be reported. This technology not only streamlines the workflow but also enhances the accuracy of classification. Additionally, artificial intelligence contributes to the detection of transient events in the cosmos, like supernovae or gravitational waves. Algorithms designed to recognize sudden changes in data streams can alert astronomers to these fleeting phenomena almost in real time. This immediacy is crucial, as timely observations can lead to a deeper understanding of these events, providing insights into fundamental questions about the universe's structure and evolution. Finally, the integration of artificial intelligence into data analysis is nesting deeper layers of complexity and nuance into astronomical research. By facilitating the handling of multidimensional datasets, artificial intelligence enables the exploration of relationships between different cosmic phenomena. As technology advances and more data becomes available, its role in astronomy will likely expand, opening new avenues for discovery and enriching our comprehension of the cosmos. Recent advancements in propulsion technologies for long-distance space travel are paving new pathways for exploration beyond our solar system. Traditional chemical propulsion is being complemented, and in some cases replaced by innovative techniques that promise to drastically reduce travel time and enhance the efficiency of space missions. One notable area of progress is the development of ion propulsion, which utilizes electric fields to accelerate ions, creating thrust. This technology allows spacecraft to operate for extended periods, gradually increasing their speed, making it suitable for missions that require long-duration flights. Another exciting advancement comes from solar sails, which harness the pressure of sunlight for propulsion. By deploying large, reflective sails, spacecraft can be propelled forward by the continuous push of photons emitted by the sun. This method offers a sustainable means of travel with no fuel required, allowing for potentially indefinite journeys deep into space. Experiments with solar sails have already been conducted, and they show great promise for future exploration missions. Nuclear thermal propulsion represents yet another leap, where a nuclear reactor heats a propellant, typically hydrogen, producing thrust. This technology could significantly shorten travel times to distant planets, such as Mars. With the capability to produce high levels of thrust combined with high efficiency, nuclear thermal propulsion stands as an exciting option for future crewed missions. Moreover, the concept of fusion propulsion is being explored, which aims to utilize nuclear fusion, the same process that powers the stars, to propel spacecraft. Although still primarily theoretical, achieving controlled fusion reactions could lead to propulsion systems that provide immense power, allowing for acceleration unlike anything currently available. As research progresses, these technologies hold the potential to transform humanity's capacity for interstellar exploration, pushing the boundaries of what is possible in our quest to understand the universe. Space telescopes significantly enhance our ability to explore the universe by providing an unobstructed view of the cosmos. Situated above the Earth's atmosphere, These instruments avoid atmospheric interference, such as light pollution and distortion that can obscure celestial observations from ground-based telescopes. This clear line of sight allows space telescopes to capture extraordinary details of galaxies, nebulae, and other astronomical phenomena. For instance, the Hubble Space Telescope has revealed images that showcase the intricate structures of distant galaxies and the beauty of star formation in nebulae. It has been pivotal in measuring the rate of expansion of the universe and identifying exoplanets in distant solar systems. By observing a diverse spectrum of wavelengths, including ultraviolet and infrared, space telescopes can detect cosmic events that would remain hidden in visible light. Furthermore, space telescopes are designed to observe celestial objects over extended periods, which results in capturing more light and revealing fainter specimens. The ability to monitor changes and gather data over time helps astronomers understand the dynamic nature of the universe. This long-term observation is critical for studying phenomena like supernovae and the behavior of asteroids and comets that pass near our planet. The technological advancements in space telescope design, like those seen in the James Webb Space Telescope, are expected to take our explorations even further. With its capability to view the universe's earliest galaxies and unveil secrets of planetary atmospheres, the potential for new discoveries continues to grow. As our understanding deepens, space telescopes remain vital instruments in unlocking the mysteries of the universe. Mathematical models serve as essential tools for scientists seeking to understand and predict cosmic phenomena. These models provide a structured framework in which complex variables and relationships can be analyzed. By employing mathematics, researchers can describe the fundamental laws of physics that govern the universe, such as gravity, electromagnetism, and thermodynamics. Through these equations, scientists derive predictions about how celestial bodies will behave under various conditions. For instance, consider the modeling of planetary orbits. Isaac Newton's laws of gravitation allow for the accurate prediction of how planets move in relation to one another. These models take into account numerous factors like mass, distance, and velocity, providing insights into phenomena as diverse as the timing of eclipses or planetary alignments. Similarly, models are employed in the study of dynamic processes, such as the formation of stars and galaxies, where the interplay of gravity and radiation pressure plays a critical role. Another fascinating application of mathematical models lies in cosmology, the study of the universe's origin and evolution. The Big Bang model, for example, relies on a set of equations that describe how the universe has expanded over time. By analyzing the cosmic microwave background radiation, scientists refine these models to gain insights into the universe's early conditions and large-scale structure. These mathematical explorations help frame our comprehension of dark matter and dark energy, two enigmatic components that dominate the cosmic landscape yet remain largely mysterious. Ultimately, mathematical models are not simply tools for making predictions, they also allow for the testing and verification of scientific theories. By comparing model predictions with actual observational data, scientists can confirm the validity of their hypotheses or adjust their models to accommodate new findings. This iterative process fosters a deeper understanding of the universe and reinforces the dynamic nature of scientific inquiry. Fractals play a crucial role in enhancing our understanding of the universe's structure by revealing patterns that recur at various scales. The concept of fractals describes complex shapes that can be split into parts, each of which is a reduced-scale copy of the whole. This self-similarity can be observed in numerous natural phenomena, from the branching patterns of trees to the formation of galaxies. When scientists study the universe, they often find that it, too, exhibits fractal characteristics, suggesting that the same underlying principles govern structures ranging from the smallest scales to the vast cosmos. One significant aspect of fractals in cosmology is how they can help explain the distribution of galaxies. Observations show that galaxies are not randomly placed throughout space. Instead, they form filaments and clusters that resemble the branching structure of a fractal. This organization allows astronomers to model the large-scale structure of the universe and understand how gravity influences cosmic formations over billions of years. By identifying these patterns, researchers can make predictions about the future behavior of cosmic structures. Moreover, fractals assist scientists in analyzing data from astronomical surveys. As they map the universe, the use of fractal dimensions in data analysis allows for a deeper understanding of the universe's geometry. These dimensions can provide insight into how clustered or dispersed galaxies are, revealing the pattern of cosmic evolution influenced by dark matter and dark energy. This approach leads to significant breakthroughs in comprehending the forces shaping the universe. The implications of fractals extend beyond merely mapping the cosmos. They inspire insights into the fundamental nature of space and time itself. The universe's complexity might be governed by simpler rules than previously thought. By embracing the concept of fractals, scientists continue to challenge and refine their understanding of the universe, opening new avenues of research and exploration. Chaos theory plays a significant role in understanding astrophysical events, shedding light on how seemingly random behaviors can arise from deterministic systems. In the cosmos, where countless variables interact, chaos theory helps to explain phenomena such as the formation of galaxies, the orbits of planets, and even the behavior of celestial bodies. Astrophysical systems often consist of many components that influence one another, making them susceptible to small changes in initial conditions. This sensitivity is a hallmark of chaotic systems. For instance, when studying the orbits of planets, a tiny alteration in the initial velocity or position of one planet can lead to dramatically different long-term outcomes. The intricate gravitational interactions among stars can be similarly unpredictable, contributing to the complex dynamics of star clusters and galaxies. Moreover, chaos theory provides insights into the behavior of cosmic events like supernova explosions and black hole mergers. As these events unfold, their outcomes depend on a multitude of factors, including mass, temperature, and pressure, all of which can change rapidly. The chaotic nature of these environments results in a rich tapestry of possible scenarios that reflect the underlying complexity of the universe. Understanding chaos in astrophysics not only helps scientists comprehend how systems evolve over time, but also informs predictions about future cosmic events. By embracing the unpredictability inherent in these systems, researchers can develop more robust models that capture the incredible diversity of phenomena observed throughout the universe. Statistical methods play a crucial role in the analysis of celestial data by providing the tools to understand complex information gathered from the universe. Astronomers often work with vast amounts of data collected through observations from telescopes and spacecraft, which can include light from distant stars, temperature measurements from planets, and even signals from galaxies. By applying statistical techniques, researchers can discern patterns, make predictions, and test hypotheses about celestial phenomena. For instance, one key application of statistics in astronomy is in the study of star brightness. When monitoring the light from a star, variations can indicate the presence of an orbiting planet. By applying statistical analysis to these light curves, scientists can determine the likelihood of a planet's existence and estimate its size and distance from the star. This process relies heavily on statistical models that quantify uncertainty and filter out noise from the data, making it possible to identify significant signals amidst the chaos. Another essential area of application is the analysis of cosmic background radiation. This radiation is a remnant from the Big Bang, and its study relies on the ability to interpret subtle variations in temperature and density across the sky. Statistical methods help determine whether these variations are consistent with theoretical predictions, allowing scientists to refine their understanding of the early universe and its evolution. Statistical techniques not only enhance our ability to analyze and interpret data, but also enable scientists to make informed decisions about future observational strategies. By modeling potential outcomes and assessing risks, these methods guide researchers in choosing which celestial phenomena to study next, contributing to our ever-expanding knowledge of the cosmos. Navigating through space relies heavily on several key mathematical principles that help ensure the accurate positioning and movement of spacecraft. One of the most fundamental concepts is geometry, particularly the understanding of distances and angles between celestial bodies. This knowledge is crucial when charting a course through the vastness of space, allowing scientists and engineers to calculate trajectories that will lead to their desired destinations. Another important principle is calculus, which plays a vital role in understanding how objects move under the influence of gravitational forces. By applying calculus, engineers can model the orbits of planets and the paths of spacecraft, taking into account the changing velocities and the effects of gravitational slingshots or maneuvers. Smoothly adjusting the speed and direction of a spacecraft requires a deep understanding of rates of change, all derived from calculus. Additionally, an understanding of algebra is necessary for solving equations that describe the motion of spacecraft. Algebra allows scientists to manipulate formulas to predict future positions based on current velocities and trajectories. Without these foundational skills, the complexity of space navigation would be insurmountable, as even slight miscalculations can lead to significant deviations from intended paths. Moreover, the navigation process is also supported by principles of physics, such as Newton's laws of motion and the law of universal gravitation. These laws help in understanding the forces at play, enabling navigators to effectively plan their courses through the gravitational fields of various celestial bodies. Harnessing these mathematical principles leads to successful missions, ensuring that humanity can explore beyond our planet with precision and accuracy. The rise of space tourism is shifting our understanding of the cosmos in profound ways. As private companies successfully transport people beyond Earth's atmosphere, the experience of space is moving from the realm of professional astronauts into the hands of ordinary individuals. This transition ignites curiosity and enthusiasm for space exploration, making the idea of traveling beyond our planet not just a distant dream, but an achievable adventure. When everyday people experience weightlessness and witness Earth from above, their perspectives change dramatically. Reports often highlight guests' emotional reactions, such as awe and humility, when viewing our planet as a fragile blue marble set against the vastness of space. These personal narratives help bridge the gap between science and the general public, fostering a sense of connection and responsibility toward our world and the universe beyond. Moreover, the influx of stories, images, and experiences shared by space tourists cultivates wider interest in science, technology, engineering, and mathematics education. Young minds are inspired to engage with these fields because they see that such adventures are possible. The media coverage surrounding these journeys also reshapes cultural narratives around space exploration, promoting the idea that space is not merely for elite scientists, but an exciting opportunity available to everyone. As space tourism continues to evolve, it may further encourage public discourse about the importance of space exploration and the sustainability of our planet. The more people become involved and invested in our journey into the stars, the greater the collective understanding of humanity's place in the universe and the imperative to protect our home for future generations. Making space tourism accessible to the general public requires several critical advancements. The first major area is the development of more reliable and affordable launch vehicles. Current costs for space travel remain prohibitively high, often running into millions of dollars per ticket. Innovations in reusable rocket technology, like those pioneered by various private companies, are key to reducing these costs dramatically. By allowing rockets to be used multiple times, the overall expenses of spaceflights can be significantly lowered, paving the way for broader public access. Another essential advancement is enhancing safety measures and protocols for both spacecraft and the experience itself. While space travel has come a long way since the early days of exploration, ensuring the safety of non-professional astronauts is paramount. Rigorous testing, improved engineering designs, and comprehensive training for travelers are crucial steps necessary to inspire confidence in potential participants. The introduction of more user-friendly spacecraft designs that cater to varying levels of comfort and expertise will also help in attracting a wider audience. Moreover, Developing the necessary infrastructure at spaceports is important. Just as commercial air travel relies on a robust network of airports, space tourism will require dedicated spaceports equipped for the unique demands of launching and landing spacecraft designed for tourists. Upgrading existing facilities to handle an increase in traffic and creating a seamless experience, starting from booking to post-flight activities, will enable a smoother journey for those wanting to venture into space. Finally, public interest and market demand will be a driving force in making space tourism widely accessible. Education and outreach efforts to spark fascination with space travel will create a larger consumer base. Encouraging partnerships among private companies, governments, and educational institutions can stimulate innovations and foster a culture that embraces space tourism as a standard form of adventure, much like a trip to a distant country. Such collective advancements will ultimately make the dream of space travel a reality for many people. Private companies are profoundly altering the landscape of space exploration by introducing competition, innovation, and new funding sources. Historically, space missions were largely the province of governmental agencies. With the advent of commercial entities, there has been a significant shift toward a more diverse and dynamic approach to exploring the cosmos. Companies such as SpaceX, Blue Origin, and others are leading this charge, striving to reduce costs and increase accessibility to space. One of the most notable impacts of private companies is the reduction in the cost of launching payloads into orbit. By developing reusable rocket technology, firms like SpaceX have demonstrated that it is possible to significantly lower expenses associated with space travel. This isn't just beneficial for these companies. It opens the door for a multitude of scientific missions and satellite deployments that might have previously been deemed financially impractical. Additionally, private companies are driving technological advancements at a rapid pace. With the pressure of competition, these firms are constantly innovating, whether it be through improved propulsion systems or advanced materials designed to withstand the harsh environment of space. This constant quest for efficiency has led to significant breakthroughs that have the potential to transform how we approach space exploration. Moreover, private companies are broadening participation in space exploration. By creating partnerships with educational institutions, research organizations, and even other countries, they are fostering a collaborative environment that embraces a wide range of ideas and expertise. This diversification not only enhances the scientific output, but also inspires a new generation of explorers, engineers, and scientists, ensuring that the pursuit of knowledge beyond our planet continues to thrive. As humanity ventures further into outer space, several potential risks come to the forefront, highlighting the challenges of sustained human presence beyond our planet. One significant concern is exposure to space radiation. Cosmic rays and solar radiation can pose severe health hazards, including increased risks of cancer and damage to the central nervous system. Earth's atmosphere and magnetic field provide invaluable protection against this radiation, but once astronauts leave this shielded environment, they face potential long-term health impacts. Another critical aspect is the psychological and physiological stress experienced in space. The isolation, confinement, and distance from Earth can lead to mental health challenges. Astronauts may experience anxiety, depression, and interpersonal conflicts, which can adversely affect their performance on missions. Moreover, the microgravity environment can lead to physical issues such as muscle atrophy, bone density loss, and changes in vision. These effects emphasize the need for thorough preparation and support for individuals who will inhabit space for extended periods. The risk of space debris also escalates with increasing human activity in low Earth orbit. As satellites, old spacecraft, and fragments from disastrous collisions accumulate, the potential for catastrophic events rises. Even small pieces of debris, traveling at high speeds, can cause significant damage to operational spacecraft and endanger lives. This growing concern necessitates improved measures for tracking space debris and developing technologies to mitigate or remove it. Finally, the ethical and environmental implications of expanding human presence in space deserve careful consideration. The possibility of contaminating other celestial bodies with Earth microbes raises questions about planetary protection. As humanity explores planets and moons, it becomes essential to balance exploration with the preservation of potentially habitable environments that may exist elsewhere in our solar system. Each of these risks must be addressed as part of a broader strategy for safe and responsible exploration of outer space. Space tourism could significantly reshape our collective understanding of Earth and its environment by providing a unique vantage point from which to observe our planet. As more individuals venture beyond the atmosphere, they experience a perspective that highlights the fragility and beauty of Earth. This shift in viewpoint has the potential to cultivate a deeper appreciation for our planet's interconnected ecosystems and the delicate balance that sustains life. One of the most profound impacts of space tourism can be seen in the phenomenon known as the overview effect. This psychological shift often occurs when astronauts and space travelers see Earth as a tiny, fragile oasis in the vastness of space. Witnessing the planet's thin atmosphere, the curvature of its surface, and the absence of political borders can instill a sense of shared responsibility for its preservation. Returning to Earth, these travelers may advocate for environmental stewardship and conservation, spreading awareness of the urgent need to address climate change and resource depletion. Furthermore, the commercialization of space travel can drive advancements in satellite technology and scientific research. With an increased public interest in space, funding and innovation in Earth observation systems may accelerate. These systems can monitor changes in the global climate, track deforestation, and assess the impacts of natural disasters, leading to a more informed public and better policymaking. The rise of space tourism can also inspire future generations to pursue careers in science, technology, engineering, and mathematics. As more people become fascinated by the cosmos and our place within it, a new wave of environmental scientists, engineers, and activists may emerge, eager to develop sustainable solutions for Earth's challenges. This cultural shift could pave the way for renewed focus on the health of our planet, reinforcing the notion that from space we are all connected.